So hi, good morning. We are not many in this time slot. Hopefully people will start reaching out. But anyways, the idea of this event is being like, we know the RT is not that huge of a community, but we are nice people. And the idea of this event is to get people together, to know each other, try to help each other. It's a more friendly event. Like we usually have another events that are like the OSPM and the micro conference at Plumbers, where we try to deal into the problems that we are debating on the LKML. So it's a more hard-on discussions. This is not that event. The idea here is to make friends, to build community, and to chat about the problems that we have every day, and to share knowledge. So feel free to make questions during the presentation. Feel free to reach out. That's the idea, to build community. And the first presentation is with Sebastian, whom he maintains the perimeter T. And yeah, here he goes.
But it's
too
5
early.
to 9. It's 5 to 9.
It's 5 to 9. My watch is wrong. It's 5 to 9. No, it's 3 to 9. Yeah, my watch is. Those old watches. That doesn't synchronize. Yeah, so we have some more hope for people reaching. Yeah, no, it's just mechanical. But yes, let's wait for the people. And I will adjust my watch. So, so for the questions, because we are recording it, I will bring the microphone for the people. So wait for the microphone before making the question, so we have everything in the recording.
Good. Cheers.
My computer is there.
We can. Daniel, you want switch?
Oh, do you want to use your? Oh, sure.
I didn't say want, I said I could.
It's whatever is better for you.
I mean, I do have the sticker, right?
Sorry?
I have. Come around. See the sticker.
Ah, okay. But if anyone wants stickers, I have stickers. You have an HDMI cable?
Yeah.
USB-C?
No, not so much. Good that we talked about it, right?
Sorry?
Good that we talked about it.
So while waiting for the slides, I will repeat what I said before. I started earlier the conference because my watch was wrong. So welcome everybody. Now we have a better number of people in the audience. And so as I said before, the idea of this event is to be like a more friendly event where we can chat, we can get to know each other, we can ask our questions during the presentation and try to build a community. We generally have 2 or 3 events about real time during the year. We have like the events like at the plumbers or the OSPM conference where we do more harder discussion on the scheduler, like what we are doing now in the LKML. And but the idea here is a little bit different, is to share our experiences and to build community. So feel free to ask whatever question you have, and we will try to address in the best way. And yeah, and so it's with you, Sebastian, now for you.
Start, right?
Yeah. Oh, by the way, for the questions, we are recording it. So before asking questions, just raise your hand. I will bring the microphone so people in the stream could listen to the question.
Hi, I'm Sebastian. I'm giving a talk about how not to break RT, like what not to do in order to make it worse for your application. My voice is bad. I could lose it. I hope that I do not. It's just so you know. So let's start. We tried to mainline RT for quite some time. And the idea, basically, mainlining it means we would be part of the upstream release, and all other people using the kernel would be aware of the changes we made. And once everything is upstream, one wouldn't have to necessarily make any changes release to release, like upgrade the whole queue. Just basically use what's already there and maybe do some slight changes because things broke during the merge, like things happen from time to time. And then we could also do the testing against Linux Next and see fallout early and not at the end, by the time I get to rebase the whole queue. So this is basically the whole motivation behind it. And from RT point of view, we don't look at any specific subsystem in particular. What we look at is the userland. We want to schedule userland as fast as possible from the point in time when the application wants to be scheduled based on the wake up to the point where it actually got scheduled. And to make that happen, we remove preemption disabled section and interrupt disabled section as much as possible. And to reach that, we do a few tricks, more or less. The ground thing is locking. Like spin lock and RW lock T is a spinning lock. In RT, this is changed to more or less a sleeping behavior. This is similar to what Mutex T offers already. The differences are that the task state is preserved. Like if you do ptrace and the task goes into the tracing state, and then acquires the spin lock, it sleeps, but the tracing state is preserved once it wakes up. And this is like an important difference, because then from outside, you don't see a difference if the task went sleeping while acquiring the lock or not. And even if it sleeps while waiting for the lock, the task is not allowed to be migrated to another CPU, which would happen with the Mutex T. And this is important aspect because the spin lock owner, like the spin lock on non-RT, is always running, so it cannot be migrated to another CPU. So this behavior is also re-implemented more or less. And this also means that the CPU via hot plug cannot go down while there's a task waiting on that CPU, which waits for the lock. And these are all the little details that are slightly different to a real mutex, but are semantically the same what spinlock T provides. And with the change, the lock owner can be preempted by a higher priority task. One of the things is that if there's a precious lock that everyone goes after, it can happen that the task that owns the lock gets preempted, and the next task that tries to acquire that lock gets also blocked on the lock, and so one task after the other gets blocked. And this doesn't happen with non-RT because they disable preemption, which means the lock owner remains on the CPU until the lock is released. And to cope with this detail, we have something called auto preempt, where the lock owner remains on the CPU for as long as possible. The only difference is if the high priority task pushes off, then we hand over. Back in the previous releases, we called it preempt lazy, which was a different implementation. But now mainline tries to get rid of cont rescat and solve the problems they have with it with the auto preempt thingy. So this is where we from RT try to piggyback on it to use the same feature and have way less patches to maintain. Interrupt handlers. So since these locks are sleeping, the interrupt handlers are threaded. Most of them, like almost every driver that you have, gets a threaded interrupt. There are differences like for drivers or hardware that needs run in hardware interrupt context. This implies real hardware that handles the system. This includes a few like the timer interrupt itself and the perf events that we have that trigger usually non-interruptible interrupts. And those have this special marker that you use and mark that those interrupts may not be threaded. And we don't have many users of those. The vast majority interrupts are threaded for the device drivers, and they're okay with it. On the other hand, since the hard interrupt controller, hard interrupt handler must not sleep and has other limitations, the things that you can do in those handlers are quite limited. The next difference is the soft IRQ handling. The soft IRQ is usually the piggyback after the hard interrupt. The idea usually is that you do like the important thing in the hard interrupt context, and everything else that you still need to handle, you lay off to the soft interrupt, which is then handled with interrupts enabled. So you could still go and handle other interrupts before you continue with the soft interrupt. This was done before we had threaded interrupts. So semantically, you could more or less move everything to the soft interrupt. There are still exceptions with it. One problem we had earlier was that once you raise the soft interrupt, especially from hard IRQ context, which is usually not happening because most drivers are threaded, the timer is a difference, for instance, then the case of UD gets activated because it's the only thread that can continue processing the soft interrupt. Because the hard interrupt has, as I said, limited things that it can do. And once the case of UD was active, it consumed all pending soft interrupts, which meant for RT workload, things could delay because the case of UD has get other priority, meaning like every other task, it's get other. So it competes with every other task for CPU, while the threaded interrupts have higher priority and are usually preferred. This change in recent releases, since the networking folks were bothered by the behavior. So now it's changed since even if KSFUD is scheduled for running, but it does not run yet, the soft interrupt will be handled right away. And this limits a few problems we had on RT with this regard. HR timer, usually invoked in hard interrupt context as well. Those as well have to be moved, and we move them into the soft interrupt context so they can, again, sleep while acquiring locks and everything else. The examples like the perf timers or timers used by the scheduler, which need to run with interrupts disabled, which need to fire as soon as possible, those have a marker when they need to run in hard IRQ context. Most of the other drivers are basically fine if it's run in a soft interrupt. The timing is more or less the same. The thread is high prior, so it gets early scheduled. Things like clock nanosleep, which is used by the task to sleep for a certain amount of time, is handled differently. For instance, if the task is get other, the wake up will happen from the soft interrupt, which might be delayed. However, if the task is RT priority, then the wake up is done immediately. Basically to lower the overhead of the wake up as much as possible. And the task with the RT priority is important, so this one are handled right away. The get ADA are less important, so they can be delayed. Basically not to build up latency if a lot of those are woken up at the same time or close one after the other. The next thing we toggled was IRQ work. It had more users than I thought it would have, but it was originally introduced for perf, so they can handle wake-ups from NMI, because NMI must not have any, must not acquire any logs because they could spin or be blocked by the owner itself. So what happens is that they basically trigger a bit to trigger an interrupt, which then has a lockless queue to add items that have to be processed after the NMI. This has been used also by other drivers, for good or for bad. For instance, PrintK needs a wake up for the printing thread or for the klogd daemon to notify userland that there are things happening that need to be printed. This cannot happen from any context. This cannot happen from within the scheduler because it will break it otherwise. However, doing it from the interrupt handler itself, it works. And this is like the thing that on non-RT, most of the things are happening in a real interrupt context. But again, for RT, we have to move it to an interrupt threaded handler to serve those, so they can be in a position to acquire sleeping logs and so on. RCU callbacks are more or less the same as with non-RT, but we have a tiny little bit of special treatment. First of all, we had to remove them from the soft interrupt because they are sometimes long running, which led to other problems. The callbacks itself can be preempted, which leads to a problem, including that the RCU section can be preempted. That if the reader is preempted within its RCU read section, the RCU machinery stops and waits for it to continue. But on RT, the high priority task can take over and delay RCU for quite some time. And for this, we required something called RCU boost, basically to lift the low priority task out of the RCU read section. And once it's gone, then the things can continue and move on. And then there are also other things that can be used on top, like the callback CPU can be offloaded to a different one, so the CPU that's designed for RT workload can work in peace and not be bothered by RCU anymore. A few things that work on non-RT but break on RT. One of the things is something I would call spin until ready. The basic situation is that you disable preemption, and not explicitly, but you inherit it by spin lock, which basically means you cannot go off CPU. And then in this context, you add a special marker that now I'm active, and you do one thing after the other. And the other CPU basically, or the other thread, spins on this active bit and waits until you leave it so it can also operate on those things. So basically this shared resource is more or less locking, but done all with own primitives. Now this works on non-RT perfectly. However, RT gets this scenario that the preempt disable that you did as part of spin lock is not disabling preemption, so you cannot rely on those things that used to work as is in non-RT. And then you set this active bit by 1, and then this other thread gets and preempts you because it's allowed, and spins on that bit. And if the thread has highest priority, then this other thread that got preempted gets never on the CPU, and you spin basically forever. Those things were mostly found in the in the core code. Like del timer sync has this thing where it tries to remove the timer from its list. But if the timer is actually running at the time, then it spins and waits until the timer is complete. And from non-RT point of view, the timer can only run on a different CPU. But on RT, the timer could have run on the same CPU and get preempted by the thread that does del timer sync, because we do preempt timer and soft interrupts and everything. And the same scenario happens with sec count and other primitives. And for RT, we had to tackle each one of those and provide something as a synchronization point of view, which means if you do del timer sync and the timer is running on the same CPU, we need to make sure that we flush them out and make sure it completes its thing, and then we can delete it, just to make progress. And most of the things we did have like unique solutions, like for del timer sync and HI timer. The difference is, for instance, for the sec counts, since those are usually more or less open-coded, we had some effort to generalize the API and make sure to pull in the logs they're using, simply that we can reference them from RT point of view and avoid the whole spinning situation. We didn't change all the primitives. Like if the driver is using local IQ disable, interrupts are getting disabled. If preemption is disabled explicitly, the preemption is disabled. All of those things increase the latency if you try to schedule, because you are not allowed to. Most of the users access per CPU variables or something that is local to the CPU. And for most of them, we had to find a replacement how to deal with this without using preempt disable explicitly. And local lock, which was introduced into the kernel, was also often a nice replacement because it handled those things nicely. In regard to this, we have more or less a log ordering. This is documented in the kernel what types of logs we have, which switch in which direction. And if you acquire them, you usually go from the first one to the last one in terms of ordering. So you go first for the sleeping logs, which always sleep, like the mutex. Then you go for the sleeping logs, which sleep on RT and RT only, like the spin log T. And the last one in the section is the raw spin log. Otherwise, if you go for the raw spin log first and then the spin log, then you could sleep while acquiring the spin log. So this is not working. Another thing is that you cannot mix like disabling interrupts and acquiring spin log, because it's not the same anymore. This used to work on non-RT, but things like that break RT. So those things need to be abstracted or use their proper locking primitives. In general, you could go ahead and try to move everything from the spin log T that generates a warning and go for raw spin log T. This in turn means that the section is not preemptible anymore. And in most cases, it leads to more problem over time. And the code you can handle in those sections is limited. And the more time you spend, and the scheduling time frame gets longer. And some of those can be bounded by the amount of items you handle. And most of the time, the driver is not ending up in the hard interrupt context anyway, so the raw spin log T is usually not required, since most drivers are threaded. So from the driver's point of view, it should work with the spin log T most of the time. And this is what will happen from a warning point of view. Like if you disable preemption on your own and then you try to acquire a spin log and you have debug atomic enabled, this is what the kernel will spit on you. And it's really nicely done. It says what it is, what it has, and what it did expect. So in this case, preemption was disabled by function here, and then RT's pin lock was invoked. And RT's pin lock is this replacement for spin lock, which is otherwise used on non-RT. Moving further, memory allocation is different. Memory allocation means with GFP atomic on non-RT, you can acquire memory even with interrupts disabled, with preemption disabled. For RT, we had to make some choices, and we ended up that you must not acquire memory if interrupts are disabled, if preemption is disabled. This would require that you need non-sleeping locks further down in the memory allocator, which then it gets problematic because you have to inherit all the lock chain down to the body allocator, where you add pages and remove pages and collocate them, replace them, and this can take up time. And we were going for the whole kernel and auditing things, and none of the code really required to have memory allocations within code that is running with in atomic context on RT. So we mostly lifted all of those, and we had in RT back in the day a few tricks that you could still free memory from atomic context. But by the time we tried to merge it upstream, the MM folks were against it. They wanted to get rid of it, and we moved on and pointed towards them. And it worked out nicely in the end. One enhancement we got into RT, into LockDep because of RT, is the thing called raw lock nesting. This is disabled by default because it leads to false positives, mostly by printk. And the bad part is that this already happens during boot if you have console printing enabled. And at that point, LockDep becomes useless, because once LockDep finds something, it disables itself. What proof locking tells you is that if you have a non-sleeping lock, like the raw spin lock, and then you try acquire a sleeping spin lock, then it will show it to you like, usually like the lock contention things it usually shows, that which lock got acquired in which order. And it's basically just a hint for you to avoid those kind of things. Speaking of printk, each driver can decide if it can work with the raw spin lock or the spin lock T is doable. Most of the printk work we have, it's outstanding and we already solved in the past, comes from the thing that we cannot use any console driver with a raw spin lock. And the reason is this basic use case. Like if you need to print a small string with 20 characters onto the UART, and most of the time the UART driver stuffs everything into the FIFO and then waits until it gets out. And at this specific baud rate, alpha 115,200, it takes roughly 87 microseconds for one character to be sent out. And the message with 20 characters gets to 1.5 milliseconds, which would mean that the driver disables interrupts for 1.5 milliseconds. And since most people look for latency times for less than a millisecond, usually like 100, 200, 500 microseconds, this is not working at all. So for that reason, we have to find a solution to get printk working, but without using a raw spin lock. Therefore, each driver can remain with his sleeping spin lock, and we can still have printing from atomic context with interrupts disabled and with interrupts enabled. Now, latencies. Most of the time, they come from context which disables preemption for one reason or another. The context is atomic on RT, and this can come from things like cache flushes. We used to have on x86 one opcode which flushes the caches of the CPU entirely and invalidates them. And this was often used in GPU kind of drivers. And the result of it was that the CPU was off for like 250, 200 microseconds because it had to flush all its caches to the main memory and then read it again. And at that point, the CPU stalled. And this was not working. Another thing is if a ROS pin lock is heavily contended, and it basically one CPU waits to get a lock and then another one waits. Situation got better with the tickets pin locks as implementation, but in the end, if the more CPUs a system has, the worse it gets over time. If every CPU is waiting for it and it waits until each one of them gets the lock, unlocks, release the section, and can move on. One example of this thing is an example of what happens if you do clock nanosleep, say with 100 tasks from RT task, which has a lower priority than cyclic test in this example. What you see here is you have thread number 1, which is the important one, which I remove all the other information from the output. So basically you see thread 1, the PID, P95 as a priority, and there is an interval of 250 microseconds, which means cyclic test gets invoked every 250 microseconds. And then it looks when should I have been woken up and when have I been woken up. And based on these statistics, the best case scenario was 2 microseconds and the worst case scenario was 27 microseconds. And as I mentioned earlier, the clock nanosleep is a function which suspends the execution of the task, and then the wake-ups comes exactly from the hard interrupt context. And if I spin 100 tasks, then it means 100 tasks with a lower priority than the cyclic test here, but still RT priority gets woken up from the hard interrupt context, which means in this first scenario, it wakes 100 tasks one after the other, and it needs 26 microseconds. And if you boost this up to 500, it's the maximum time it needs is 75. If you go further to 1,000, you are at 347. 5,000, it's almost 4 milliseconds. And this is the point that if you have a ROS pin lock and a small amount of items you work in your loop, you don't see it as a latency problem. But if you can influence at some point that you get more and more work items to work on, then you see it goes through the roof with the latency. And this is like the point where we had to make the switch. The RT tasks get woken immediately, but the other tasks get delayed to the soft interrupts so they can be preempted like after each wake up, so you wouldn't build up the huge latencies. If you end up in a situation that you need to figure out what is going wrong, you have your cyclic test, you have tracing, and you can go and start looking what is happening in my system and what is the root cause of the issue we're having. Daniel here came up with the RTLL tool, which basically combines the tracing points and a few other things together and tries to help you with the analysis, like what happened in my system, when did it start to go bad. And I have here a link where a reporter came on RT users, reported that he has a latency problem. And Daniel suggested to use RTLA, give it a try, because it was newly merged at the time, I think, like 1 release or 2. And the user had the recent release with RTLL. He used the commands and found the issue in the next post, right? Yeah, this is the thread everyone can look at and maybe use it one day. Another thing we have in RT is priority inheritance. This solves a lot of issues. It makes some worse, mostly related to soft interrupts. And the reason is that the expectation within the soft interrupt framework is completely different than what we have everything else. The basic way how priority inheritance works is that you have task L, which is the low priority task, and it owns a lock. And then it gets preempted for some reason by another task. Then task H, like the high priority task, wants the same lock. And the only thing it can do, instead of spinning, it hands over its priority to the low priority task. So L, the low priority task, is now elevated to a higher priority. And this is only for the time being until the lock is released again. And then everything gets back to normal. And the reason is, instead for the high priority task do nothing, basically inherit its priority to speed up things so it can get back on CPU and do what it was supposed to do. This is basically a graphic of it. Like the low priority task is running, then it has the resource acquired, and then it gets off CPU at point 3, and the high priority task is running. And we have middle priority, but this is not important. The important part is that at point 5, the priority was inherited by H to the L task, so it got lifted in the hierarchy, was able to run, and after the task was released, it got off CPU, so it was waiting until H completed its doing. To see this in action with tracing, this is what it would look like. This is with the SCAD switch and all these scheduling events reduced to a bare minimum. So you have the locking task L, which locked the lock, and then locking H got woken up. And you see at SCAD switch that you moved from priority 89 to 79, which means in kernel terms, the lower number means higher priority. And you see previous state is R+, which means the task did not leave the CPU because it was done whatever it was doing and asked to sleep, but it got preempted. Then H got on the CPU and asked for the lock as well. And since it was occupied at the time, it did this SCAD PI set priority, which means it inherited its own priority from 89 to 97 for the locking L task. And then, since it was the highest priority task, and H itself had priority, the previous state is S, which means this one goes voluntary to sleep. And then task locking L is the task with the highest priority. It unlocks the lock, and then SCAD PI set priority goes back and reverse the 79, and we go back to 89. So if you want to see how does it work, do we have it, do I use it in my system, you can basically go for PI set prior and see what is going on. And PI boosting works for most of the locks. Most of the locks are based on RT mutex, which means the spin lock T, the mutex T itself, all of those have priority inheritance within the kernel. For user space, you have to use the set protocol function from the libc and set the attribute, the priority inheritance. Otherwise, it's the other lock which do only sleep and wait, and then glibc handles everything and the kernel cannot do anything. So for priority inheritance userland, you need to change the protocol. For kernel, it works everything what we can do, which means RWSM and RWT cannot be handled. Or it works partially. The thing is that both of them can have multiple readers at the same time, and we cannot boost multiple readers at all, because we don't have any handle and we cannot boost two tasks at once from the same log. Therefore, only the writer can be boosted by the reader, but this is usually never the case. Soft hierarchy context is getting worse with priority inheritance. And we have preemption, and because of it, what we end up with is a big kernel log, but not the one that we had in that past, but one that is a big kernel log CPU-wise. The thing is that we have soft interrupts like take soft IRQ at task click in a timer. And what we have is that they may have CPU resources which are per CPU. And they are not protected at all. They are not even known that they need protection. But the assumption is since years that once a soft interrupt is running, no other soft interrupt can run. And this means the resources are protected implicit. And to cope with this, we introduced a local log within local BH disable, which basically when soft interrupts get handled. And the good thing is that we remain bug compatible with what we had in mainline. The bad part is that we can have soft interrupts that build up work and the work is not handled. And then if you have like one networking card that is more important and needs to do things regularly, and you have another networking card which is handling bulk traffic like SSH for copying large files. And if those things run on the same CPU, then what basically happens is that the periodic traffic from your high important task gets blocked until the bulk traffic is completed. And a few things are done in soft interrupts to tackle those things, but none of those are visible on RT because of the priority inheritance. Because what happens is that the high priority networking card inherits its priority to the bulk traffic, which then gets run completely for milliseconds or seconds until everything is done. And then after all this completed, the real-time traffic can go on. And this is not what we hope for. I started working to resolve the issue and to add more locking within soft interrupts so that we don't have this one global lock per CPU, but identify resources which are shared and require explicit locking. I presented this last year at Plumbers, and the networking folks were those ones which I tried to sell this, mostly because networking is their highest user of soft interrupts. There is no other subsystem that is using it that much and relies on its assumption as networking does. And the idea was to convince the biggest user of it and then have everyone moving on with it. And the first two versions were not what the community expected. And now I'm working on a rework which should be more or less what I asked for on the last review. And yeah. Another problem that we end up on RT is basically tasklets is the thing where you can delay work from interrupts to soft interrupts, and the same thing is doable with work queues. The problem is more or less that once your work originated in a specific context, like a specific driver, once you hand it over to a work queue or to a soft interrupt, this work becomes anonymous. So you had your threaded interrupt running in a specific priority. You cannot inherit this priority to your work queue, and then your work could stall. This is seen sometimes in the TTY driver when you have you try to do real-time communication over UART, because they hand out work to the K worker. Basically, it starts with a high priority interrupt, and then it's get to anonymous context and you have no idea what happened. And for most of the things, we try to avoid K-worker as much as possible and only handle things that are not time critical. Now, to summarize all those things we have, from driver's point of view, it's usually enough to basically stick with a default spinlock T and avoid everything else where the API, where you put expectation within the API, like spinlock T disables preemption on non-RT. Just don't rely on disabling preemption. Try to have a design, a scope, what you need to preempt, what you need to lock and why you need to lock it. And if you need a lock that's only CPU-wise, then you can use the locks and use this for your resources. And also not to add more primitives to soft interrupts or K-worker, where you lose the power of your execution context. And if you need something to spin off work, there are other ways to do it, like K-threads. And those things add maybe more context switches, but in the end, you end up with more power over how you schedule your work in the end. This would be it. Any questions so far?
Hello. Yeah, firstly, great talk. Thanks for that. A lot to absorb. I had two questions. So the first question was, what's the vision for drivers? Are they supposed to be the same between RT and non-RT kernels? Or are they supposed to be aware that, yes, I'm running on an RT kernel and make changes? I can think of one example, like, you said in RT kernel, all the IRQs are threaded. So now the threaded IRQ has a priority, and should the driver care about it and make some, adjustments?
The driver should never adjust the priority.
Okay.
This is decision making. This is department of userland. Because it might work for your use case.
Or userland, okay. So userland should find the threaded IRQ and then adjust its priority.
If this is needed, yes.
If this is needed, okay, that's the strategy, okay. So the driver is expected to be the same, whether used in RT or non-RT, but the userland knows that it's running RT and it makes these adjustments.
Exactly, yes. Because you could have networking and you could have storage.
Right.
And you could say storage is not as important as, then you would lower the storage interrupt or increase the priority of your networking stuff. And then this is like your use case.
Right, so it's application or use case control, right? So
exactly.
Okay.
And it's not limited to RT. You can use threaded interrupts as a boot command argument, non-RT as well.
Right, okay, right. Cool. Okay, my second question is, I saw in one of your slides, there was a screenshot that showed it's a QEMU machine. So I was just curious that how useful is QEMU for RT development, and where can you use it and where should you not use it?
What slide?
One of the slides you had.
I wasn't there yet, right?
It was a little bit ahead, yeah, somewhere midpoint, I would say. Yeah, that one, yes. It did say hardware name is QEMU standard PC, right? So
it shouldn't be useful for RT because on RT you see if you have sleeping while atomic, then you see all of those. This is useful for non-RT because you see the warnings that you would have seen on RT,
okay.
but without RT.
Okay.
So this was the motivation behind it.
Got it, okay. All right, thanks.
Oh, thank you. I'm curious about your mention of libpthread. There was this big problem where futexes didn't allow priority inheritance that was discussed a lot a few years ago. And is that problem fixed? Is that what you were saying with your comment about the pthread libc priority boosting, or?
Can you give the mic to Jan?
Yeah, so the issue is that condition variables in combination with priority inheritance mutexes don't work with glibc. It's not solved in glibc, but RTPI, librtpi, it's now a package for Debian. My colleagues were working on that. So you can use the library. I think it was once started by Darren Hart. And it should make its way into distributions, more distributions. So Debian has it now in testing, if I remember correctly. And others should pick it up as well, or Yocto recipes, or you look at.
No,
To my knowledge, no.
Futex2 is a different department. The thing is that with conditional variables, you need another log. And this was the old implementation of glibc, that you need a log within the conditional variable to add and to do maintenance. And this log was a regular log. And this is when you don't have with the priority inheritance, and then you go to sleep if you get preempted in this particular spot. And Darren Hart made the patches like years back. And then they got delayed for, And then glibc upstream reworked that code. And now they don't have the log. So now not really, because there is a race condition because you need a log for, right, and you don't need it that often as you used to have. And to have that log, they spin on a bit. And I try to reproduce it, but it's tough. But if you audit the code, you will say this can log up. But not as often as you did with the old implementation. Exactly. And the library Jan mentioned, Darren started on Plumbers. We finished it in Austria. And then NI took over, and I never heard of it again. Yeah, I'm not saying it's not used, but they finished it as far as I'm aware. And they're using it. And that's all that's left, my knowledge.
Yeah, librtpi is still a thing if you want to use it. I am currently maintaining it. I took over from Darren. It's on GitLab and GitHub now.
Is it in Yocto or anywhere?
I don't know if it's in Yocto yet. We are using it in Yocto, but I don't know if we ever upstreamed the recipe for it. I don't think so. But we could. We should.
Quick follow-up. It's just from the awareness perspective. I saw that also internally. People are generally not aware of that issue because it's now, I think, 16 years old. The glibc bug is, no one knows this. But raising the awareness for that is one of these nice little traps you can leave behind when writing real-time applications, and people run into that. So it would be good to have the visibility this way as well.
Yeah. I did do an EOSS presentation 2020 you can find. But yeah, you're right.
Need more mics.
So he said he gave a presentation on ELC in 2020.
Yeah.
Yes, please.
My question is less technical, but this demonstrates it. I think there, by the way, it's a great presentation and a lot of good information in the follow-up conversation. I think I see a lot more, the interest in preempt RT and developing for this is picking up. Maybe there's a discussion for us as we go through the day, but for developers that are maybe new and not part of the core, should we direct people to, I'm developing an app, I want to do it on preempt RT, where do I get all the guidance or the tricks in, that sort of thing? So I don't know if anybody has.
So we try not to rely much on tricks, and everything should work more or less out of the box.
Well, he's right. We should, but there is, maybe tricks is not the right word, but maybe it's,
We do have a wiki where we document a few things, like what you should do, like the priority inheritance thingy, like lock your memory, like how to initialize an application. And sometimes people come with other things, and I point them to that wiki, and if they come up with things that don't work as they expected, to update the wiki or hand me over the materials so I can do it myself. And there is little feedback from that point of view. And I don't want to blame people, but mostly the industrial people is like, it works for me, I'm done, I'm gone. Whereas the other open source people, like less industrial, they usually contribute more and or fix up the documentation or things like that. And we don't see that often.
Got it. So yeah, maybe it's something we can, throughout the day talk about how maybe we would point more people to the wiki or, how we do that, right? Good question.
I think it is. The question was, is librpi on the wiki? And I think it is.
Action item. Check.
You checked. Well, so let me have a to-do item for today then.
Yeah. Last question, because then it's time for the.
So this would be really dumb, but I don't have any experience in RT, but I find it fascinating. I'm curious, sorry, totally lost my train of thought. Wow, totally broken. Where do I learn about why the kernel isn't real-time compatible normally? Why do I have to apply real-time patches? It just feels like from the education I got when I was an undergrad was you should be able to make a kernel real-time normally, but clearly it's not for some reason. Has anyone written a good article or a good understanding of why the kernel isn't already real-time preempt compatible?
I mean, all you need is an interrupt, like hardware interrupt. It takes a millisecond or two because the register isn't popping up right away. And the next thing is you have an IO MMU and you need to map memory, and this takes a while. And all those things build up the time the CPU is blocked and cannot schedule away towards the user application.
I guess, yeah, it must have been too long for me because I would think you would just let the CPU go do something else. That's what I don't understand is why don't you go do something else while those hardware things? Yeah, okay.
I mean, the easy answer is it's trade-offs. When you have the kernel in the preemptive mode, you context switch more, and then you added an advantage on the latency, but you add a penalty on the throughput. Same thing with locks, same thing. So it's always trade-offs. The vast majority of users are not real-time. That's a reality. So they're looking more for throughput than real-time. That's why the preemptive RT was for a long time a pet set, because it was trying to bring this advantage for latency for a small community without breaking the main community, which is the non-real-time. So the effort is, how can we make this preemptive mode part of the kernel without breaking the large audience?
I think that's what I was at. That's what I personally would like to read more about that if there's someone that has a good article or something.
I mean,
Yeah, I'm not sure there is, but I think the other way, I think agreeing what you said is, what your point is, and I think this comes up a lot, is that you can engineer a system to be real time without this before, but you had to be very, very careful and not a lot of other things going on and on and on and on. Is that what your point, right? So this is making it, more part of the system, and more people want to have, more modern and other things can be going on, right? So a lot of it comes down to the system engineering burden, right?
Yeah, I think we are over time now. But that's the idea of the event, is having these discussions, and that's the idea. It's good.
Okay,
So thank you, Sebastian. Yeah, there's an HDMI. E alla fine è andata, dai.
So, okay. So welcome everyone to the second session in RT Summit. It will be easier than Sebastian's talk, but in the same vein. So the topic of the talk is if you are developing a driver for Preempt RT or just submitting a driver open source, how do you know that when RT becomes mainline or even with Sebastian releases, probably your driver will not cause a problem and it will work as smooth as it is intended. So there were some questions about why mainline is not hard real-time compatible, and I hinted at that actually at the start. So because we are different from plumbers, so the audience is more generic. So when people usually talk about Preempt RT, there is first the kernel releases, which people call Preempt RT, which basically say 6.5 minus RT1 minus RT2 and so on. But then people also, when people say Preempt RT, that's also the preemption model in the RT releases or when RT becomes mainline. So the Linux kernel has multiple preemption models, and Preempt RT preemption model is the most preemptible, where most of the kernel code paths, as much as we can be preempted by higher priority tasks, including user space tasks, and that's the point. So what's the main benefit of Preempt RT? Why do people use it? The main difference between a classical RTOS or even an RTOS which actually has POSIX compliance, like Integrity OS and others, is that with Preempt RT, we give you a guarantee or an almost that all of the existing mainline drivers, unless there are bugs, should be working as usual. That's the first part. And the second part is that the standard Linux user space works as usual. So all of the well-known components above the Linux kernel should work with Preempt RT. And this is the main benefit over others. For people who might have worked with RTOSes outside of Linux, even when they claim full POSIX compliance, usually things do not work out of the box as it is claimed, especially with proprietary RTOSes. And then what Preempt RT also provides is that, okay, so you can run your standard Linux applications and databases and whatnot and graphics applications and all of that, but then you can also have your own real-time application with hard real-time priorities. And what the Preempt RT kernel does is that it makes most of the kernel code path is preemptible. So actually your application, when it needs to run ASAP, let's say there is a signal from a certain sensor, then the Preempt RT kernel can preempt the existing code path, run your application until it relinquishes the CPU due to sleeping or any other mechanism, then goes back. And that's basically Preempt RT in a nutshell, because there were some questions to Sebastian talk about that part. So what I will do here is provide a short summary of some of the main things that were done driver side in the last 3 years. I will cover sequence counters, which is a lockless mechanism, and some of the tasklet API changes and some of the trouble we actually got. It's solved right now, but there are some issues, and some of the custom drivers code and why hopefully we should not have that in the future. So to start with sequence counters, it is basically a lockless mechanism where where you can ensure consistency by readers retrying until the data is valid. So what you typically have is you have a write part on the left, and this is, for example, there can be more readers. So here is one reader, and basically the reader keeps retrying until the counter is even, which implies that actually the data section is valid, and then it can read the data. And this is mostly used for data that is read much more than it is written. This is, for example, statistics and network drivers. There is a large amount of sequence counter usage and similar data. So for preempt RT-wise, now the Linux kernel had sequence counters for a very long time. But for preempt RT-wise, there was the issue that there were two issues. And the first one is the write section always needs to be protected within itself, right? There cannot be multiple writers to make sure that the data is consistent. So there is some write serialization mechanism. But then preemption needs to be disabled so that the readers don't leap forever. And the moment we disable preemption, when we talk about preempt RT, the moment we are not happy, because disabling preemption means latency, right? Remember the slides I had four slides ago when I talked that you might have your user space application and it wants to respond to an event. So in any case in the kernel, if preemption is disabled, then practically speaking, your RT application is blocked. And that's actually latency. Exactly this is what latency is about. And this is the whole purpose regarding the questions on the previous session, the whole purpose of RT. We want to make sure that we run your application as soon as it wants to run. The second problem was that since we in preempt RT want to make that path actually preemptible, then there is the risk of the read side looping forever. Because what happened is, imagine on a single CPU and the write side is working, and then within the write section, a preemption happens because your application, for example, wants to respond to a certain event. And your application then does an innocent system call, which goes into whatever subsystem in the kernel. And then, unluckily for you, this code path hit the read path of the same sequence counter that was preempted. And this means that the reader will actually loop forever and the kernel will be blocked, and basically this core is now over. So that's a kernel bug and the core is dead. And what we did in RT around 2 years ago was that we made extra safety mechanism so that if we are in RT and we know that the preemption model is the highest preemption model, which is preempt RT, which basically the most preemptible model in the kernel, then we actually do extra sanity checks to make sure that we don't loop forever. And the result of what we did 2 years ago was that not only we made sure that the existing drivers are still working, but we also enhanced the API in a way that actually made sure that there is more extra lock-depth integration, so that what happens is not only that we fix the problem on preempt RT without disturbing the existing drivers, but also mainline has the benefit of actually extra lock-depth checks. And after that, there was also something called latch sequence counters, which is a special variant of sequence counters that were only used in very delicate code paths in the kernel. And then we also formalized that and added some extra sanity checks. And then the rest of the kernel actually began using that API after it got formalized. So this is one of the patterns. The second pattern was tasklets. So the kernel, or let's call the core kernel locking group, wanted to actually get rid of tasklets for a long time, but the number of call sites are extremely huge. And there is also this problem in the that was existing before, is that tasklets had a certain call that's called tasklet disable or tasklet kill, which means that you can send the signal to actually say, okay, I do not want to respond to, I don't want to run my handler even if there is a pending signal. And like what happened with sequence counters, this also has the same busy looping problem. So imagine that you are at the tasklet handler, and then again, because preempt RT makes all the code paths as preemptible as possible, so you get preempted, and then you go to a code path which calls tasklet disable on the same tasklet that was preempted, okay? And the problem is that implementation was actually busy looping. So again, you hit the same problem of busy looping while, and then the core is basically dead forever because, okay, that's another kernel bug. And we hit this kind of looping mechanism in a lot of areas, and this is one of the most common patterns. So there was also certain code paths in VFS where there was the same pattern, and we also had to invent mechanisms to actually avoid this problem in RT. So to do that, and this also shows you a sample of how we work actually in preempt RT. So like preempt RT looks a little bit simple from the outside, I would say, but actually we do really like hard work or extremely hard work to make the kernel work with all this preemption involved. So actually for this single problem of killing a tasklet, the same tasklet that was originally preempted, we actually surveyed 400 plus call sites. And they are all drivers. There were 400 drivers. And we couldn't actually automate. And we wanted to know, what we wanted to know is the context of tasklet kill, tasklet disable, preemptible or not? Because if it is preemptible, then we don't need to busy loop anymore. That's our problem, right? So if we don't busy loop, then actually we can solve that issue. And we surveyed manually the 400 drivers across everything, networking, graphics, drivers, SCSI, and we discovered that actually all of them except 10 call sites were calling the tasklet delete or tasklet kill from preemptible context. And then what we did to avoid that problem was actually to use condition variables and normal sleeping mechanism instead of busy looping. And then this actually broke this busy loop pattern. And I want to stress that this is a big part of what we do in preempt RT. We always try to, because the moment you have a preemptible code path and then you have any sort of infinite loop, the moment you risk killing your CPU basically. And this is in sequence counters, tasklets, and various other APIs. The other call sites where they were actually using tasklet, killing tasklet from atomic context were actually buggy, and we also fixed those. So, and then all of the tasklet API is now working under the hood without anyone noticing with preempt RT as well. And tasklet in general, so there is a lot of ongoing work to remove tasklets from the kernel. It's still ongoing. So yeah, there are some things that can only done through tasklets, and the network subsystem still uses part of these things. But we hope it can be deleted in the future. So.
Who is getting rid of tasklets?
So there was a submission on February, actually, Tejan. So
No, he just relabeled it.
okay.
So it's like you take an apple, you make it orange, and then you say it's not an apple anymore. But if you remove
So
the
it's
color, it's still an
internally-
apple
okay.
underneath.
Okay. Okay, so, and we still also want to keep all the hooks about deleting the tasklets and disabling and all of that.
Well, you could move one by one to Tejun's API,
Yeah.
but nothing changes. You still have K-worker with disabling the work thingy. And yeah, so this doesn't change. WorkQ doesn't have the problem because WorkQ has a raw log for enabling, disabling, and scheduling for its maintenance.
Mm-hmm.
And tasklets may have long looping parts that they don't even have logs for it.
Yeah.
So that's the other part. If you have long looping parts, which WorkQ doesn't have, then you need some kind of other synchronization.
Okay. And yeah, in preempt-RT wise, we will still, yeah. So this is part is done. There's no to-do elements in the future.
Well, we could, I mean, I've been looking, networking doesn't do tasklets, by the way. I'm not aware of, there are certain drivers that do WorkQ and tasklets and an API, and this is different. SCSI has a lot of drivers that outsource to tasklets.
Yeah.
And they have also this poll thingy, which is an API copied by Christoph. And it's all the thing to deal with the problem that they get many IOs and they don't have many queues.
Mm.
Because networking, you come and get a certain queues, like 20, one per CPU, and you don't have much of this problem because you don't monopolize the CPU then. And then people started doing tasklets, and not because they thought it's nice.
Mm.
But you could move it to a threaded interrupt and then be done with it. But then the SCSI folks are not so easygoing in changing the core code.
Yeah. Yeah, because also my understanding that they wanted also to maintain some locality on the cores and stuff like that.
This depends.
That's the SCSI, yeah.
This is, yeah. But you can still have, let's say, worker on the same CPUs, on the same core. That's not a problem.
Okay, okay.
But yeah, go on.
Yeah. So, yeah. So, yeah, so that's basically regarding the tasklet part. And the most important, actually, for me regarding this talk is because people are a little bit confused about the preempt-RT part, is that if you really use the standard kernel locking APIs, and if you really use them as they should be used, and do not depend on implementation details of such locking APIs, we do all the hard work for you. So we only hit problems when drivers are kind of overly smart, doing something that they should not be doing. There were, for example, during the sequence counter work, a lot of drivers which open-coded certain lockings, and because they thought that their own implementation is better than the standard kernel locking mechanisms, which is not true, not just only from a performance perspective, but also from a locked-up perspective, because the moment you do your own locking, then you lose all the kernel infrastructure and validation and so on. So, yeah, so this is what mostly, and then when RT also becomes mainline, this is also expected to be the goal. So the moment any driver to be submitted which actually breaks on RT, and most probably, if this is not an RT bug, then we hope that the driver will not be merged because it's not respecting the kernel locking APIs and so on. So there was also, and this is the same pattern of drivers being overly smart or drivers trying to do low-level checks or low-level implementation, is checking the context. So there were some macros that were added by the lock-in subsystem and certain parts of the scheduler to check the context, whether it is, are you in preemptible context, are you in hard IRQ context, are you in soft IRQ context, and the problem with these macros was that their semantics actually was different according to the preemption model of the kernel. So whether you have like preempt RT or you have other preemption models, then the semantics was different. And even if you have something like config preempt count, and if you have a certain number that can actually, for example, preemptible might return always false, and then some drivers and some subsystems were actually using these macros to automate memory allocation and so on, to doing the memory allocation whether through GFP kernel or GFP atomic and stuff like that. And this also hurted us considerably during preempt RT, and we did also the same thing. So just like the tasklet use case, where actually if you download the slides, there is a link to a Google Sheet where I show the survey, all the surveys that we did. We also surveyed all the call sites. And for example, in the SCSI subsystem, there was libSAS and certain other components where we had to manually pass the context to the APIs, and instead of making the APIs act smartly and try to find the context and adjust the memory allocation accordingly. And the benefit of that, we actually added rigorousness, and for each commit, we actually showed the full context analysis of all the call sites, and then we had a proof that the driver or the driver subsystems don't actually need that much to do all these context checks. It's much better to actually be explicit about it, know your context, and just submit it as a parameter according to the call site. And the same with USBs and so on. Probably the last thing that's actually now in modification in driver's land is the print K ongoing work, so regarding atomic consoles and so on. And this is actually most of Sebastian's patch queue right now, all the console locking that was added. And there were also some code in graphics drivers and so on in DRM and i915 and so on, where there can be open-coded, for example, disabling and enabling interrupts, and instead of, for example, calling spinlock IRQ save and so on. But after actually the print K merge, the full merge with all the drivers mainline, then again, we stress that if your driver is using the kernel locking APIs as they should be, and do not and does not depend on the implementation details of the locking APIs, but actually implement on their their specification, then your driver should work out of the box. And that's actually the entire job of preempt RT. All what preempt RT wants is to utilize the existing wealth of all these drivers that has been written for 15 years for all the different architectures. And with all that, still run all the standard Linux user space and then provide hard latency guarantees for high priority real-time applications. And yeah, and that's basically it regarding drivers and preemptor T. If there are any questions, I would be happy to answer, and I would also be happy to answer the question that was the last question in previous session about why preemptor T is special, and yeah, if.
Question?
All these problems with
Yes, sorry.
all these problems with open coding. Okay. And
I'm not sure if it's recorded, but I can hear it, so I don't.
oh yeah, all these problems with
Thank you.
open coding and sequence counters
Yes.
and weird ways of re-implementing context switching. Is that something that, with static analysis, like maybe with CoSNL, we could automate detection of those things? Or would that just be too hard because all the weird things that people have done are too different from one another?
So yeah, so when we actually do the surveys, we use CoSNL at certain parts if it is simple parameter swapping or if it is really a repeated context. But all what we did in the sequence counter stuff, the information was actually all dynamic and not static. And this is why we had to go through all these hoops where we actually change the internal locking implementation. So when we do, for example, the survey for tasklets, we had to do the 400 drivers manually. And like I shared the sheet with Sebastian and like we divided like 200, 200, and then we had to check each one manually because we couldn't actually automate the part of knowing if the call site context is preemptible or not. So we wish it can, but we still, in a number of cases with these surveys, we cannot yet.
But one thing I would like to add is, first of all, you have to see things that fall apart. Then you know what you have to looking for. So we have seen a case where the tasklets looked up because of the API. And then we had a workaround for it for years. And then we tried to solve it properly. And then we had to look exactly for the tasklet thingy. The same goes for the other parts, like in interrupt. Most of the people using it were not doing it for the reason they thought they were doing it, right? And so if you want to help the open coding at some point, sure you can do it, but you have to know what you're looking for. And the best way is actually to abstract it with the API so that the people don't try to open code it. And nowadays, if you switch the preemption model and it fails to compile, then you already are at the point that it doesn't compile anymore because of the open coding that is not working anymore because the members are gone, are different. And then you are at the point that the K-robot may reply to your patch that this isn't compiling on RT, and you're done with your extra work.
But that also assumes that the open coding depends on internal details. So, for example, the sequence counter stuff was failed during runtime, so not even during compile time. So, yeah. So.
Yeah, so I think my question is fairly generic that now that preempt RT is getting really close to being in mainline, right? What do you have to say about the other approaches with, moving all the real-time stuff into another core and with Zephyr or any real-time OS, right? At which point do we decide that, well, that doesn't need to happen because preempt RT is here?
Yeah. So we have customers who actually do that through certain mechanisms, for example. So through some hypervisors, like embedded hypervisors, and statically partitioning the system. Here is like, I want this core to have like my RTOS, FreeRTOS, or other RTOS, and Linux does that. And for example, the jailhouse hypervisor, you can actually do exactly that and provide all the safety mechanism. So you don't even need to do hacks, like it's well prepared for that. So there is a place for this, and this depends on your use case. So, and also depends on, is your real-time application like a Linux application, or is it just something small? So the whole benefit of this picture basically is that when I say the real-time applications here, these are still standard Linux applications, and we require you to do some stuff like in the locking and the POSIX APIs and stuff, but it's very minimal, and we have it in the RT Wiki, just like 5 steps. So this is where it depends on your use case and your latency requirements.
Yeah.
Yeah,
Just
for sure.
adding one on top of this is that when you have this idea of partition in the system, there is an orthogonal feature of the Linux that helps, which is CPU isolation. Nowadays, the CPU isolation can deliver like almost fully isolated. There is a tool that is a companion of the timer.lat, which is EOSS noise, that helps to measure how much noise the operating system is adding into an isolated CPU, where you could confine your real-time tasks isolated. And it's in the order of 20 microseconds every second. There is even a change now that I'm doing on the kernel to help in this case with the real-time throttling, but it's good enough for the vast majority of people.
I have a very specific example. So I have a specific common example, which is audio, right? I mean, a lot of audio needs to be on Linux, but still a lot of SOCs have their own RTOSs running on DSPs and things like that.
But audio is actually a really good example of this, of the preempt RT case, because actually, like on the Linux RT users mailing list, we have a lot of users who submit bug reports who are professional audio people. They are not even programmers. They don't know like the Linux details. And in that case, it's actually really helpful. So I worked actually in Pulse Audio and a little bit in Pipewire, and then it's really helpful to actually have real-time priorities for the RT parts of these audio mixing daemons. So this is actually, so this example is actually a validation of the preempt RT model, not the other way around. And also one thing regarding the static partitioning, so when people do static partitioning, it's also, and thanks Daniel for the correction, you are correct actually. It's not only for performance, also for safety and standards compliance and stuff. So sometimes people want to have their RTOS like certified by certain, there are multiple safety certifications, and then there is a benefit, not just a performance benefit, which as Daniel said, the numbers are close, but also, safety verification benefits until the ELISA folks like go on, but the ELISA is still R&D at this moment. Yeah, so. Did that answer your question?
Yeah, so
yeah.
If we don't have any more questions, we can do a pause, have a coffee, and return at the 11, which is the next slot, right?
Okay. Thank you, everyone.
Yeah.
Thank you.
Is that 11, right? Okay, yeah, see you all at 11.
You mentioned something about CPU isolation. Is that like for the non-real-time kernel as well?
Oh, yes. No, that's a pretty standard
feature. Okay.
Yes, it's been since I remember using Linux.
I had a question after we wrapped up, but
Yeah, for
do you
sure.
do any type of like hardware testing?
In what way?
Well, like, okay, so we make changes to all these drivers, right?
Yes.
But how do we know, like, I mean, logically that it makes sense that they would be correct, but is there any type of like physical testing of the device?
Yeah. So most of the common use case hardware-wise is that you usually have a sensor like a camera or a laser or something like that, right?
Yeah.
And you want to respond as much as soon as possible.
Yep.
And a lot of our customers actually, for example, because we are in Europe, we are in Germany, so a lot are these European industrial customers, like in Italy, for example, these massive tomato sorting machines. No, seriously.
Yeah.
And they want to make sure that they can process like multiple tons and stuff like that. So, and in that part, like the testing is both hardware plus software, right? So you have the driver, and what they usually do is that they actually measure the. Oh, no, thanks. Yeah.
So good morning yet. My time zone is in Europe. I was about to say good afternoon. So, so good morning. I'm Daniel. I work at Red Hat. I'm a senior principal software engineer there. I'm part of the real-time team inside the kernel core team. But most of my work is upstream, helping developing the kernel. I work with helping maintaining SCHED_deadline, which is a real-time scheduler in the kernel, doing tooling like the real-time timer.lat, the RTLA timer.lat, here and the runtime verification subsystem. And yeah, today it's a more practical presentation. Ahmed, is it yours? Yeah. Yeah. So today is a more practical presentation where I show how to use this tool to debugging the real-time scheduling latency, mainly for the parameter-RT, but not only. The tool works also for the regular kernel. So this is an introduction. I think I don't need to convince people here that Linux has been used as a real-time operating system, right? And the motivations are mostly because nowadays the software stack for these modern real-time operating systems, they are being developed for Linux natively, and people are trying to migrate like old code to run on Linux to have access to these new kind of libraries, like for example for AI and all this new cool stuff. And because there are many people that understand Linux, but also because, or mainly because Linux nowadays achieve a good timing behavior, both for latency and for response time in the case of real time. And some key features that help to enable that is like the fully preemptive mode, that is the parameter-RT, or the real-time scheduling with SCHED_deadline and so on. So one of the problems, however, is that now that we have this new class of tools that would like to use Linux as the operating systems or the embedded systems, right, is that one of the problems is the way that we show that the timing properties of Linux are met. Okay, over the years, Linux has been tested using like a black box approach. That is, there is a tool that simulates a real-time behavior and it measures the execution, the metric, like the latency. And then there is a report saying, okay, my latency is 10, my latency is 200, right? And it's okay, it works for development, but it's not enough for many use cases, right? So just to show what was the state of the art, now like when we see tools like cyclic test, the idea is that you have a measuring thread. This thread sets a timer for the future and go to sleep. And then when this timer in the physical world, it happens, when the time reaches there is the hardware wakes up something and blah, blah, and then the thread is scheduled, right? So in this black box approach, like cyclic test is this, the hardware, the timer hits the time, and then it's scheduled this thread that is the highest priority thread, so we have this latency. So the black box approach, it works, but it has some drawbacks. And the main one is that it gives us no root cause. And the root cause is generally done using tracing, right? But these tracing features are not that accessible for non-expert users because you need to understand how the kernel works and how to interpret the trace. It's very easy to go there and enable too many things, and then by adding too many things, you have too much overhead, and by having too much overhead, you break your analysis and so on. And I mean, after 10 years for me doing this by hand, I get annoyed, right? Say, how can we change that? But anyways, who cares about this thing, right? Other than the guy doing debugging at Red Hat for 10 years. So the point is that nowadays with the merge, we have like the real time to the masses, in the sense that all the kernel developers, for example, we need to care about the RT metrics, because if they do a change in the kernel that breaks the parameter-RT, now it's the breaking the kernel itself, because parameter-RT will be part of the kernel. But not all the kernel developers would like to become a real-time kernel expert, because they have other complex things to understand, like file system. I don't understand about file system. And they probably will not be that interested on trying to understand why I'm breaking the RT. But there's also like, there are many new projects that people that people need the kernel to make them possible, like real-world projects. For example, in the automotive, people on the ELISA group trying to show the why the Linux can achieve the latency, or people in automation industry trying to run virtual PLCs that have this cadency very precise. So there are many people reaching to the real-time kernel. And it's hard to think that everybody will become a real-time kernel expert, right? So we need to build tools to facilitate people's life. So what is the timer lat? So it's a new approach to this idea. So breaking down this tool into pieces, it has like a kernel and user space components that tries to automate the measurement and the root cause analysis for the scheduling latency. So in the kernel side, we have a kernel tracer that is optimized to have as low overhead as possible, to not influence too much in the latency metric, right? So we have this tracer. The name is the timer lat tracer. It's a kernel tracer. And it has also some trace points that are based on the EOSS noise tracer. And here you have a academic paper published at IEEE Transactions on Computers, where I explain like the internal parts of this EOSS noise tracer, trace points, and timer lat. Okay, just out of the scope, but this paper has been like the most accessed paper in this journal for almost 1 year. It's a nice thing. It's open access in this journal. And so we have this tracing infrastructure to measure the latency, and a workload simulator. That is, there is kernel threads that simulate that real-time workload to measure the latency it suffered. So that part's in the kernel. It's more kernel experienced people. But then to try to make that kernel part accessible, there is a user space component. That is the RTLA timer lat tool. So RTLA is a suite of tools to analyze the kernel behavior for real-time Linux analysis. And inside of it, there is this tool which is timer lat. So it's a benchmark-like interface for that in-kernel infrastructure. And it has like two skins, let's say. There is a skin that looks like the top tool that keeps showing you interactively what is the latency of the system, or to build a histogram to make a more statistical analysis. And the tool also has an auto-analysis module that I will show later how it works, but that can give you the root cause for a bad latency. And it also has the possibility of having a user space workload expressing the kernel. There is kernel space and user space workload. So just a practical intro. So do you remember that previous example where we have like the measuring thread that sets up the timer for the future and wakes up? So it uses basically the same approach here. There is a measuring thread that can be in kernel or user space, you choose, and it sets a timer in the future. When this time comes, like the hardware will set the signal to the operating system that is raising an IRQ. On the timer lat, we have a special IRQ that handles that timer. And so we can already start measuring what is the latency for the IRQ. And then this IRQ wakes up the thread, and we can measure this latency, which is the total thread latency. We'll get into that later, explaining more. But just have an overview. So here is one example of the tool running in a system. It's my developing box. It's running a kernel compilation in background. That's what is on that terminal. And then I will set the tool, RTLA timer lat. This is the top skin. And it start measuring the latency. In this side here is the IRQ latency, and this is the thread latency. The thread latency is similar to the cyclic test output. And it gives like what is the current latency, what's the minimum latency, the average and the max for the thread and for the IRQ. And here you can see like the overhead is very minimal, just have an idea. So here the minimum latency is 2 microseconds. So even though it's tracing in the background and collecting data, it's not influencing that much in the system, or barely nothing. So that is the top interface, and this is the histogram interface. So just limiting to the CPUs. So here it is dispatching the workload, dispatching the tracing, collecting data, and setting the histogram collecting in the background. Ahmed? tell the microphone. Sebastian looks grumpy, but he's a good heart.
So when you talked about the measurement thread, was it in user space or in kernel space?
You can choose in kernel and user space.
In
Here
both.
in this example is in the kernel, but you have the user space as well. And it has another fields in the at the end. I will show that.
Okay, thanks. Thanks. Yeah.
From the scheduler standing point, it doesn't matter that much. For example, in the sched deadline, I don't look if it's a kernel or a user space thread, for example, on the RT as well. It's just that when you are a user space thread, you generally inherit some configuration like C groups, and that influences.
We had cases where people, for example, was using like some mechanisms like timer FD to put their handlers, and then this is where extra latency was induced just because the user space mechanism chosen. So this is why.
No, it has in kernel
Yeah.
and user space,
Yeah.
both cases.
Yeah. Thanks again.
So that was the interface like a benchmark. But when we are debugging the system, we generally have a maximum acceptable latency. That is, on my system, it's working fine as long as it's like less than 100 microseconds. If it's more than 100 microseconds, I assume it's a fault and I need to analyze it. And that's where the magic starts to happening. With timer.lot, I can set it to stop if the latency is higher than a number. And then if it hits that case, it will print an output saying, okay, here is the root cause of the problem. So you can set it if it's for the thread, latency higher than, or the IRQ latency higher than, or there is a magic option that is -A that will try to enable for all the things. So if it's thread or IRQ, and we'll try to use the full options. Like, let's say, the best options for this analysis. So here's one example of the timer, of the analysis. It is set to stop if it's more than 30 microseconds. It just started running, and then it immediately stopped. And here is explaining the root cause. And in the presentation, I will explain what are these components, and that's the idea of the presentation. Just having a look. The auto-analysis output, that's where we started looking at what is the root cause for a bad latency value. So the auto-analysis that print at the end, it tries to decompose the latency into a set of variables. And which variable can be analyzed more or less independently. And this is based on a research I presented in 2020 at the ECRTS conference, also at the Plumbers. There is background for these variables and why they are independent, but just skipping here for the time of the presentation. So IRQ and threads, they have different analysis. So the auto-analysis, it prints parts for the IRQ and part for the thread. And the auto-analysis here, it works for the parameter RT, but also for the non-parameter RT kernel. It's generic. So to understand the auto-analysis, we need to understand some set of abstractions that people use in the real-time theory. So basically, execution time is the time required for you to accomplish your work. Like any work that you need to do in the kernel, or any task, they have its own execution time. The blocking time is the overhead or the delay caused by tasks that have a lower priority than your task. Interference is the other side. It's when something with a higher priority causes a delay. Blocking lower priority, interference higher priority. So in Linux, even though we think on Linux tasks as threads, like user threads, process threads, when we start analyzing deeper, we can see that there are other contexts where work can run, basic context. And these we can consider as independent kinds of tasks or different types of tasks. So we have NMIs that have its own context. We have IRQs that are its own context. These soft IRQs can be said as its own context, but on the parameter RT, they became thread. So they're not that relevant for the RT because they become thread. Still, it's here because of the non-RT kernel where we have software queues. And the threads themselves. So these are just the base components to understand the auto-analysis. Here is one example of an execution of a timer lot that was set to stop if it's more than 50 microseconds, right? And it stopped because of an IRQ. So here is the output. How do I read this output? So here I created a timeline explaining what happened, right, for the explanation here. So the IRQ latency, that is the time for when the hardware raised the IRQ from when the handler started working. In this example here, the IRQ latency was 32 microseconds, right? And this was when the thread was, when the IRQ handler for the timer out was able to read the time. But a little bit before it, the handler started working. And the handler started working 31 microseconds after the expected time. So what could cause this delay for the starting of the IRQ handler, right? Blocking, something that with a lower priority that was running there before. And in this case, there is this blocking thread saying, okay, this was the thread that was working. A thread has a lower priority than an IRQ, so it's blocking. So what thread was running there? It was like this, okay, this object2 task. And when the IRQ happened, this was the stack trace. So what was that thread running that caused the delay for my IRQ handler? And see here, this part of the stack trace is the stack trace of the IRQ handling, right? That from the things that set up the handler so the handler can start working. So this is part of the execution time, so it's not the blocking. So what was causing blocking? There was this write system call in the Btrfs that for some reason inside the C group code disabled IRQs inside of a raw spin lock. That was things that Sebastian was explaining before. So there was a code here that disabled interrupts using raw spin locks, and this caused the delay for my IRQ handler. What was that? So with this starting point here, one can start debugging the system more precisely. Boom, why does this IRQ disable inside the C group, inside the write system call? And then one finds out that, okay, there is a patch in the kernel that added this change. And one can blame Sebastian because it's Sebastian's patch. Sorry, Sebastian, for this example. But then one can also see, okay, this is a legitimate use case. Go ahead.
Did I break it or did I fix it?
It's not your fault.
But why do you point towards me if it's not my fault?
Oh, no. No, in this example, let me finish. Let me finish. I'll save you. I like you. So in this example, you can see that this is a legitimate use case for disabling the IRQ. So if one would like to have a lower scheduling latency, they either would have to rework this code to make it even smaller, or try to avoid this code stack in the CPU that it's running, right? But the example here is that we can, from just simply using the tool -A50, we can get an information that points us reasonably well to the direction of what is causing the problem. And that can save a lot of time, lots of time. Mainly in the use case, for example, where we have at Red Hat, where we have customers running the system, and then they file a JIRA, a call. Okay, my system is having this latency. If they run timer.lat with this option, they will give us a starting point. And this starting point is already like a fingerprint for the problem, because it's very likely that the problem that this person is hitting is the same problem that someone else already hit. And the benefit of always running all this infrastructure, always tracing, is that we never miss a case of, okay, I saw a latency, a spurious latency, and it happened, and I'm not tracing. So I don't know what happened that time. If I start tracing next time, it could be yet another problem. And then we find that problem. And then we say, oh, I'm glad I fixed the problem. And then they start running back again, and there is the previous problem yet hitting. And this causes a lot of frustration. Lots of frustration when you are supporting use case. So trying to always have the trace and always having a fingerprint of the problem helps a lot in the process of supporting people and supporting workload. And we have to be fair. Most of the people delivering a real-time system is interacting with other people that are the actual users of the system. And trying to clean up this communication brings us a lot of calm and peace of mind and confidence on what we are doing. So there is another abstraction that there is in the tool, which is jitter. Jitter, or release jitter, is something when something is delayed not because of blocking or lower priority or because of interference, higher priority, but something outside of the scope of the operating system. And here is, for example, when we have like a system that has not, that doesn't have like an exit from idle setup, like disabling P states. When this is detected by the tool, it's saying, okay, there is an IRQ latency of 40 microseconds, but the tool, the thing that was running was swapper, it was idle, right? So why is idle creating this problem? And then here's problem, it's pointing, it's exit from idle. And it also shows, okay, maximum IRQ latency from idle, it's 40, so okay, there's a problem in the idle setup. So it's always pointing two directions. There will be more and more analysis added to it, right? This is just 1 year of work added in this kind of analysis inside of it. But the more we collect these analysis inside the tool, the more we will keep accumulating the knowledge. Ahmed?
So do you also detect cases where the firmware steals the CPU from the kernel? Or?
That is added, or that's analyzed with another tool inside the RTLA, which is the hardware noise.
Yeah.
And then that's in the final slides. I talk about that. Oh. But yes, there is a tool to help on that case. There is even research on that case for when we use virtual machines. So here's one example of the thread latency. So we have a case where the IRQ handler latency was barely 0, right? It was negligible. The IRQ latency was just 1 microsecond. So okay, the IRQ was very fast. There is something on causing a delay after the IRQ. In this case, I'm not using the real-time kernel. I'm using the regular kernel, so we can exemplify it better. So it's the non-RT kernel. So the IRQ duration, the execution time of my handler was 9 microseconds. Good, it's not that bad. But still, my thread latency was 500 microseconds. What was running there in the kernel that caused this latency? But before going there, you see the interference, that is when this thread was awakened and when it started running, there were higher priority things running on that CPU causing delay. What was those things? There was IRQ, another timer IRQ, right? Local timer, 3 microseconds, nothing. There were some soft IRQs, the timer soft IRQ and the RCU. This is the amount of interference that they added, still low number, like the percentage is very low. And we also had a thread running on that CPU before my thread was able to run. And it was the migration thread, which is a special kernel thread that runs at the highest priority. But it also added just a very low latency. So yet again, you need to look at the blocking thread. What was running on that CPU? In this case, was a K worker running the compressed pages inside the Btrfs. So we can say, okay, that was the thing that caused the latency. How should I deal with that? One can either move this unbounded K worker to another CPU, removing it from that CPU, or one could try to add it, like check a conduit scad inside this code. So the tool is pointing where the problem is, and then a person can start working from there, like more precisely. So that's the idea. It's not yet fixing the problem. It might fix with AI. No, not yet. We still have job security. So, okay, that was the auto-analysis. The auto-analysis, it analyzes traces, but there are other things in tracing that we can use to debug the problem, because tracing has an infinity of options, like lots of trace points. that can help me understand the work queues and what was the thing being scheduled and so on. So the RTLA is a timer lot. The RTLA timer lot is a front end for the tracing tools. So it has natively the support for enabling these trace options. The basic things are these trace points here. These trace points are part of the EOSS noise tracer, which inside the code, the timer lot tracer and the EOSS noise tracer, they are basically the same tracer with different workload and name, but they're all in the same file. So it has these minimum events here that are responsible for creating this analysis. It's just these trace points. Why? Trying to reduce the overhead. And these trace points, they do in-kernel processing to understand what was the duration. It tries to remove the nested overhead one to the other. There is information on that paper. It's too long to go into details here. On that paper I mentioned before, it has all the whys and why it saves time. But with these trace points here, we can create that analysis. And here is just one example of the trace. I run the timer lot, stop if it's more than 30 microseconds. You see here it will run, it will stop. Here's the auto-analysis. Oops. But you see here there is a trace file at the bottom. And this is the raw ftrace output. And see, you see the events, the stack trace. The tool makes it beautiful in the auto-analysis, but you can also read all the tracing information raw from here. But that's not all. As same on TV. It's not all, because we can also enable the other existing trace points in the kernel to go deeper in the analysis. So we can enable other trace points. We can create filter for these trace points, and we can create triggers like for histograms. Timing allowing, I will reach there. So here's one example of running YouTube. Better quality, please. So here is that previous example, but it's also enabling the SCADing trace points, the work EQ trace points, the IRQ, the Intel IRQ trace points, regular IRQ trace points. So it's running the same thing, but giving more information that we could analyze in the trace. As you can see, I'm not a good YouTuber because I could have run this faster. I probably, show the trace. Go ahead, Daniel, show the trace. Yeah, okay, there's the free on page comment. That was the blocking thread. The problem is that if I try to push forward here, it will leave the full screen. Okay, so reading the trace. As you can see here, we have way more trace points now. And then you can go deeper in the analysis, editing, piling up more things. So there is this IRQ work. That's the latency reported by the tracer. There is like the SCAD waking, the SCAD wake up events. So you can go in deeper and piling up things. So even more than that, we can use other tracing things to figure out more statistical data. For example, on ftrace, we can collect histograms of things. And these histograms can give us valuable information. Here, in the video, I will show you copy and paste the command line that is in this page. Right? It's a very long command line. So here's copy and paste probably. Come on, YouTube, better quality, please. Yeah. So just copying this very long command line. So it's saying timerlot, the top version of timerlot, and it's enabling the EOSS noise NMI trace points and creating a histogram for those trace points of NMIs for the execution time of the NMIs. Also for the IRQs, I would like to create a histogram for all the IRQs that I can show the execution time of all the IRQs. Same for software queues, same for thread. So as the system is running, an interesting fact. So it's running, collecting histograms, and these histograms are being saved in these files. But you can see here, it created a little bit of overhead, but it's just 1 microsecond more, right? Because there is always this trend, editing more tracing, editing more overhead. But as long as this overhead is bounded to an acceptable value, it's okay. And at the beginning of the presentation, I showed like 2 microseconds as minimum. Now, even enabling all the trace points information and collecting histograms, it's just 1 more microsecond of overhead. It's acceptable for the kind of information that we have here. So, for example, it is showing that during that execution, there were NMIs on my CPUs. And these are the execution times of the CPUs, of the NMIs. So, for example, there is an NMI that took how long was it? So there was one NMI on CPU 23 that took 9 microseconds. In the CPU 22, it took 10 microseconds. So it means that at least if this NMI happened concurrently with my timer, I would have at least 10 microseconds of latency. Now, having a look on IRQs, other IRQs. So you can see here, there is all these, here is ordered by the CPU. On CPU 1, there were these IRQs. On CPU 2, there were these, and CPU blah, blah, blah. And here is the execution time of these IRQs. There was, here is the example, 32 microseconds. There was, in the CPU 23, in 22, there was one, CPU 22, there was one IRQ that took 32 microseconds. It was a timer IRQ. Right, so if this was the timer IRQ of my timer lat thread, and at the same time that this happened, an NMI happened, my latency can compose already to 42, 10 plus 32. And then we can start speculating on these values and try to compose the latency from the worst values that happened during the execution, but not necessarily my sampling thread got to that case. So we can compose the worst case latency from the things that didn't happen in the worst order, but could have happened. And that links to the research I did in 2020. It's in part here, not all. And here is the histogram for threads. So the blocking thread for the threads, they were lower than the IRQs, 10 microseconds, 11. So here, let's see, probably in the video, I stop in the video where I see a very large number. No, but you see it's around 10-ish. I think there are cases of, let's use 10 here. So there was these 10 from threads, 10 from NMIs, and it was 30-something from IRQ, right? So it can be at least 50 microseconds if we get the worst case one after the other. But it didn't hit 50 here because that possible worst case didn't happen while sampling, but it could have happened. And then when we start going deeper in this analysis, we can have a better information. And the cost we see, it was just 1 microsecond more on the minimum latency. It's okay for the analysis that it gives. And as we are looking for bad numbers, it's acceptable. This is an option that instead of running the thread in kernel space, it can be in user space. But it's even more. The timer lat here it's dispatching its own per CPU threads. But you can also use any thread of your system to go to sleep on the timer lat file descriptor, and and timer lat will analyze the latency of that thread. For example, if you have like our middleware for automotive things, you can put your middleware on automotive things to sleep on the timer lat file descriptor, and when it wakes up, the timer lat auto-analysis will do an auto-analysis of the wake up of that too. Yeah. My time is running short. Here's the user space tool. It will become the default option here it's not yet the default option. Timerlat dash top dash U. It will add another variable here, which is it goes to user space, and then when it returns to user space, this is the execution, this is the latency. Goes to user space and return. So it would be the minimum time, the maximum time to give to reply to a, for example, to a network package going to the kernel space. So it's yet another metric. So instead of having one single metric, we now have a tree, and each one has an explanation for it. And see here, I think it's, yeah, histograms as well, so tree values. This talk is online, and you guys can see there's recording of it. I just need to run a little bit. So by the way, going to the end of the presentation, there are some options. We can set a different period for these real-time tasks, for these real-time threads. We can limit the amount of CPU. We can set the duration. We can, by default, it runs of FIFO 95 priority, but you can set other priorities to the measurement threads. You can use get deadline, for example. These are the options. You can set the threads to other C group, not the default one, and you can disable auto-analysis, enable auto-analysis, and so on. And by the way, that was what Ahmed said. There is this case where the latency in the operating system is what we are measuring. But there could be the case where the latency is caused by the hardware installing the threads. And so this is a tool that measures how much noise the hardware is adding to your threads. So how does it work? It dispatches a per CPU kernel threads that disables interrupts and keep measuring the time. If there is a gap in time that was not caused by an NMI, you can start blaming the hardware. So there was nothing in the kernel causing the latency, so it's from the hardware. And this is what this tool measures. It's also part of RTLA. And the idea is to accumulate these tools all inside RTLA. This uses the OS noise tracer that there is description on that paper. And this is the hardware LAT version 2.0, let's say. It's the evolution of timer LAT. So before running the tracing analysis, beware that your latency is at least this case here, because if you hit the wake up of your thread when the hardware is running this noise, it can accumulate on your latency. And if you remember, I said 50-ish microseconds. If we sum these 10 microseconds more, my latency could be even 60, even though the sampling thread didn't get it. We can start playing with these compositions. So final remarks. So our Timerlat integrates workload tracing and auto-analysis. It produces the summary for the latency spikes, and it allows the user of more advanced tracing. As I said, there are more tools inside RTLA. There's Timerlat, OS noise, hardware noise. All these things, RTLA is part of the kernel, so it's inside the kernel source. So it's integral part of kernel. All the documentation is in the kernel documentation already. And it can only get better. There is a tracer that I'm working which measures the execution time of your workload. It's based on the OS noise tracer. This work already integrates part of the formal analysis of scheduling latency. That is a research work I did during my PhD. It brings part of it. Not all, but I need to bring it. The Timerlat it measures by sampling. The RTSL, which is this work here, it measures all the things separated and then composes what would be the worst case execution time of the latency if the bad situation happened. And there's a formal proof of why this is the worst case chain of events. I have been working with Paulo Bonzini and some students on integrating these with KVM, so we can detect when the noise is caused by the hypervisor and not by the host. And there is more things to come. Yeah. This presentation is actually a tutorial. So I made a tutorial and made a presentation from the tutorial. And here's the tutorial. It's like a written version of this presentation. And I will keep updating it over time. And just, yeah, that's it. Thank you. Do you have any questions? Run, Sebastian, run!
So you mentioned sort of noise introduced by the hypervisor. I work in cloud, so we're often, thinking about issues with customer VMs and things like that. How does hypervisor noise show up in like the current tracing architecture?
So there is this tool, right? Device noise tracer. What it does, it creates it's a kernel thread. I will add it to user space support, but basically it creates a thread that keeps spinning on the time and see if there was a time gap. When this time gap happens, like on the hardware noise tool, because interrupts are disabled, it's basically only hardware happening, right? So this OS noise tool here, if you run for example, on a VM, on a cloud provider, it will show how much CPU time your task is gaining from the virtual CPU. And it shows a percentage of it. And it starts blaming if it's a thread, another thread on your CPU, IRQs, or if it's hardware. When you are running on bare metal, it can only be hardware. When you're running on a cloud, on a virtual machine, it could be the hypervisor or the hardware. Yeah, it could.
Is there any way to disambiguate between hardware pauses and like a hypervisor pause
That's a
with the
research
current
work.
tooling, or that's the future work?
That's the future work.
Okay.
That's a research work that I did with Paolo Bonzini, the KVM maintainer, and a student in Polimi, the University of Milan.
Last follow-up, I promise. Like, so, how would you disambiguate? Like, is there any indicator? Because it just is.
On the KVM, it knows when the vCPU was preempted by the hypervisor or not. If it was preempted by the hypervisor, it's something running on the hypervisor, another thread. If it wasn't preempted by the hypervisor, it's something that's even out of the control of the KVM. So it's harder.
Okay, thank you.
It was.
Yeah. So my name is Xu. I'm from ARM. Thanks for your talk and thanks for the work. So I wish I could know this tool earlier because then it may make my work easier. So I never tried this tool before, but I used the trace CMD to figure out the root cause of a large latency when I testing on the ARM server cores. So what do you think of that tool? And also that I think the tool you presented has a nicer interface for the users. And you also mentioned that I think what I really like the tool is that it can decompose the total latency into small parts. So, for example, how much latency is spent on an IRQ. But you also mentioned that the overhead is low. But how did you do that? Yeah. So just want to hear about the comments for the Trace CMD and your tools, if you do any comparison in the nice features.
Trace command, the tool trace CMD, Stephen would correct me. It's trace command. The author of the tool said, oh, it's trace command, Daniel. So trace CMD, trace command, it's an interface for the ftrace thing in kernel. Timer dot is one thing in the tracing in kernel. So you can use trace command to dispatch timerlot. You can, like the RTLA interface is one interface for the tracer, but you could also do things like this. Sudo trace command. I'm developing things. It might crash my system because I'm developing things for timerlot and I'm using an RC kernel. If it crashes, it's because of these new things, not because of the things that are on the kernel. Trace command record -p timerlot. So I'm recording the kernel events, but I'm saying I would like to use the timerlot tracer, not the function tracer. So here it's recording for a while. Control C. Trace. I see it's a development kernel. It's the RC2. It didn't crash. Trace command report. I think I need to run if sudo. You see, here's the. I can use the timer.tracer also with trace command because it's all part of the ftrace inside the kernel. The timer.trace does the same thing that the trace command does. It goes to the same interface, enables the same thing, collects the same thing. It's just a different interface. And the overhead will be the same. They're all integrated on the same subsystem in the kernel. And there was about the composition, something? You asked something about yeah. This. How you made the overlay so low? There is a trade-off. When saving things to the trace buffer takes more time than processing in kernel, it's better to processing in kernel. When it's better to use in user space, it's better to write to the buffer and do processing in user space. After doing this for that long, I figure out what things work. It's died. It died better. So there was a research on the runtime verification subsystem when I measure what is worth doing in kernel and what is worth doing in user space. And I got the knowledge that I learned on that work to figure out what was worth doing in the kernel and what was worth doing in user space. That's why it has these two components. It's trying to minimize those. And the decomposition, you can find the reason why on this academic paper. And this shows there's a theorem, or there's formal notation to explain how these things are composed. And then there is theorem and lemma and definition that composes that, and these are the variables. This is not yet part of the kernel, but it will be. Hopefully.
You mentioned that for arbitrary user space code to be subject to this analysis, it should sleep on the timerlat file descriptor. Are there code samples somewhere that shows how you're doing that, or some type of documentation?
Yeah, there's, let me do here. For Brazilians, I'm looking like Silvio Santos, but that only works with Brazilians as a joke. You see, he just looked at me. He's very kind. So, source, git, Linux, tools, tracing, RTLA. To hold the kernel. Korg. No. Korg, yeah. This is the mirror of the thing I have in the kernel. These are my scripts. Source, Linux, tools, tracing, RTLA. Sample. Here is a Python code of an application that uses the timer.file descriptor and measures the latency of any arbitrary task. And here's it's in the code, the sample. It's in Python because it's easier to understand Python, and the sample code would be smaller. It can be in any language. Yeah.
So one of our most customer requests is, I have this hardware, kernel version XYZ, I run cyclic test, I have 100 microsecond and they want 60, and what's wrong, right? And then they send us the hardware by post, and then we spend like 2 days to reproduce the problem just to start analyzing all the usual traces. Are we at a high confidence point that we can actually set a policy to our customers that no one gives us cyclic test results and we standardize that they start using RTLA first?
We are moving into that direction.
The same problem otherwise.
Yeah. We are moving into that direction inside Red Hat. Yeah, for now things are working fine. And you can use it to cross-check one with the other.
Anyone? think we have a break now.
Let's make it without.
5 minutes, 11:55 now. This thing.
Us to remove the
Test.
badge.
Test.
Okay. Somewhere here? Test, test, 1, 2, 3. No. Okay, we'll start, I guess. Others can join. Hi, everybody. This is Umesh. Again, this is an auto update mode. I don't know how to. Man. Anyone knows how to disable that? Huh? I have somehow it is going in auto update. Yeah, auto advance. Keep the slides updated. Is that the one? Oh, okay. Yeah. Thank you. Okay. So good afternoon, everyone. Good morning, I would say. 1 more minute left. So my name is Umesh. I am from Intel, and there is the rest of the team who contributed to this specific use case. Okay. I'm an engineering manager for the specific product that we developed. It's called as Edge Controls for Industrial. And the feature that I'm talking today is kind of one of the a key feature that we are delivering for most of our China customers. This is coming, the use case is coming from China. So ECI stands for Edge Controls for Industrial. The credit goes to most of the developers that you see at the down. They are from China and they couldn't travel, so I'm here to present on the behalf of them. Hopefully I'll do the justice to what these guys have developed. So I'll talk about what ECI is, Edge Controls for Industrial, and how are we basically working on the real-time aspects. We use extensively the preempt RT, and most of the time we focus on our optimizations, benchmarking. That's what I think is needed in the market when we go to the customer. Everyone knows there is a preempt RT available, there is a general purpose kernel available, but what they are looking for is for their specific use case, they want to understand that that system has been optimized. So we heavily focus on the optimizations, and we do deliver the kernel image, the whole image if someone wants to basically use. We do deliver the source. Again, it's more open than open source. The source is available, anyone can download from eci.intel.com. Okay. So what this product is, the way I said, most of the industrial customers today, what we have is kind of they have that fragmented kind of OS. They do use Linux, but there is no standardized way for the industrial customer. Today's focus is mostly the industrial customers, mostly the discrete automation, process automation. You got the robotics customer. So that's where this product is kind of focused on. So the whole idea of the ECI is making sure that we are making the easy consumption of real-time aspects, make sure that we give them the modularity. So when I talk about modularity, what does that mean? So take an example of process automation. They might not be strict on a real-time cycle time. Their cycle time requirement might be in a seconds versus when you go to the discrete automation or robotics, their cycle time are more strict. So you need maybe in a microsecond or millisecond requirements, correct? So even though they are using the same software, their KPI requirements are a little bit different. So that's where we basically bring in multiple modules inside the kernel itself, and multiple kernel configurations that you can optimize, you enable something, disable something. So that's where we talk about the modularity. And in addition to the kernel, there are other features or aspects of the software that we deliver, is making sure that we work closely for the virtualization. Now, workload consolidation has become like a big theme, and software-defined industrial system is another theme. So in the industrial domain, what you see today is mostly you have like a fixed function devices. Like on a factory floor, you will find that there are 10 devices doing 10 independent jobs. Now, the push is they want to consolidate. You don't want to use like a different hardware for different things, correct? So the biggest thing that we want to solve is on the consolidation. So that's where the virtualization comes into picture, containerization, and finally the way of deploying it itself, correct? So take an example of a factory floor. Now, if you want to bring a new IPC, industrial PC, onto the factory floor, now there is a life cycle. There is a day zero life cycle of that device. What it has to happen, correct? When you connect to the factory floor, so that's where we call like onboarding of a device. So we do provide the technologies like the FIDO. I don't know if you guys heard about that. That is used for the onboarding technology. So that's your zero touch onboarding. So overall, this is what kind of included inside the edge controls. So I briefly touched on the kind of technologies that we work on. For the virtualization, I can just, because that's a topic I'll be talking more. So in virtualization, we deal extensively with the hypervisors. So you know KVM is type 2 hypervisor, but for the real-time use cases, we need to have a type 1 hypervisor. So we go for ACRN, I don't know if you heard about that, ACRN. So it's again the open source project initiated by Intel, but now it is the community project. It is part of Linux Foundation. So we use ACRN extensively for the type 1 hypervisor. So that's where the virtualization technology lies. We do support the third party, but mostly our intention is to support the open source one. Orchestration, this is basically where you are bringing the IT into OT kind of thing, correct? So today, the way I said, there are fixed function devices, they do a one specific job. With the orchestration technology, we want to bring in like dynamic workload, basically application management. The role of that PC can be changed by deploying the workload that you want to have. Let's take an example of robotic arm today. It might be doing a job of pick and place from conveyor 1 to conveyor belt 2, okay? And at the same time, it is detecting a specific object, maybe it is doing a sorting. Now, by using the same conveyor belt and same robotic arm, but now you deploy the another workload and now ask that robotic arm to do something different. So what is happening here is we are trying to use the same hardware setup, but the different application. So that's where we want to basically bring in the orchestration technology, making sure that you can deploy those workload. We do deal with most of the OSS, making sure that we update, we rely more onto the community, mostly the LTS kernel is what we take, and then the additional patches that we put on the top of that. We do deliver those patches. Intention is always to upstream whatever the changes we do, but most of the time, if they are out of tree, then we do give those codes with our releases. We extensively work on the connectivity. TSN is kind of the big thing, time sensitive network. If you see in industry, most of the protocols are proprietary. Profinet, Profibus, if you see Siemens have their own protocol. So what we want is we want to bring in more openness. So TSN is what the big push is there going from Intel. You will find most of the the Ethernet controller like I210, I225, I226, these are supported on discrete and integrated also. So we extensively work on that one. Robotics is one of the profile of control, so we do support robotics, security and functional safety. These are functional safety, we don't do much on that one. Security is more on like Intel has inbuilt TPM. What we do is on the base of that TPM, we have the another software layer which can basically help you to run your workload into like a trusted environment. You might remember Android has that TEE, Trusted Edge Execution Environment. Similarly, let's say you have the AI workload. Now you want to protect that AI workload, so you might want to run that in a trusted execution environment. So that's where we spend some time making sure that we deliver that kind of solution. And these are the kind of verticals, businesses that we support, machine builder, discrete automation, process automation, and industrial robotics. That's kind of the high-level overview of what the product itself is. Now I'm going to talk about the use case that I'm trying to present here. So workload consolidation is the key. What our customer wants is they want to get more out of the power that we have in the CPU. Let's say there is a 8-core CPU. Traditionally what happens is you might be running, let's say, on the Ubuntu or maybe Windows. So you don't know whether you are utilizing all those cores effectively or not, correct? So that's where we bring in like virtualization technologies. So traditionally, for the RT workload, what you do is you use 2 cores. Your 1 core is utilized for your RT task, and historically these RT tasks are not big. They are maybe the relays or like a small task, but you want to make sure that you don't have any jitter for that task. And then you run most of your housekeeping task on the core, other core. So this is the historic one. Now what we are trying to do is how can we squeeze in both these tasks on the one core. The way I said, let's say there is an 8 core CPU. You want to basically run the maybe service OS on 1 core, and the rest of the 7 core you want to simulate the RT task. And in that case, now you are combining both the housekeeping task and the RT task onto the 1 core. So this was the problem statement. The use case was from the we had like energy customers. The use case was to have those 8 or 7 VMs running with the RT task. So this is kind of the high level, I would say, architecture. To enable that 8 core, what we used is we use the hypervisor, mostly the Acon hypervisor. It helps you to isolate. The reason behind using Acon versus we have other, like let's say KVM, which is type 2 hypervisor, you will not be able to do much of the isolation compared to your type 1 hypervisor. So we used type 1 hypervisor, making sure that we isolate the resources. So you are actually, what you are doing is you are pinning the task, that task to a specific core. So we do a CPU pinning for those tasks, and then some pass-through activities. Maybe you want to use, let's say, for your service OS, you want to use the graphics. So you can use some graphics pass-through, or you can have the shared graphics also. So based on your use case, you can do that. But the whole idea is we do the isolation. So that way you are trying to avoid the noisy neighbors from that RT task. So this is kind of architecture. This is one architecture, and then based on this was the use case. We had this distributed controller system. If you see here, we got 7 RT VMs, and we got 1 service VM. So on that 8 core system, we have 7 RT tasks running, and the way I said, they are very lightweighted. I might be having relay or watchdog or some other things, correct? And then the 1 core we are trying to use for the service OS. So when you have the hypervisor like Acon, you need to have the task running, the service OS task running on the 1 core. So we actually have this one here, and then most of those tasks are running are pinned. These VMs are pinned to the specific core. So this is like use case 1. The use case 2 is where most of our customer have kind of a mixed critical workload. They want to run the RT task, at the same time they want to run the non-RT task. So in this use case, I have the RT task here running on the left side, but at the same time we have basically non-RT task. So historically, if you see on the factory floor, you will find that there is a separate IPC for the HMI, okay, and then there is a separate IPC for running the critical task. So with this consolidation, we are trying to basically bring the RT and non-RT tasks together. The first use case was more on how can I have more RT tasks running on a 1 core. In the second use case, we are trying to bring in how can I have RT and non-RT tasks running together side by side. Okay. Again, because of the isolation, even though you have, I usually treat them as a noisy neighbor because they are going to create kind of a jitter, more jitter for the RT task, correct? So because of isolation, even though there is a jitter, that jitter from the right side is not going to impact the real-time task. So this is our kind of a use case 2, where this is getting adopted because it saves definitely the cost. Instead of having 2 or 3 PCs, now you can do the same task with just 1 PC. All you need to do is get the core machine with multi-core, and then use the virtualization technology. And these are the big cases that we deliver from the product that I explained you, the ECI. So we deliver this off-the-shelf like a BKCs which can run on a specific platform, and then the customer can basically extend that to the choice of their platform. Okay. Again, this has the hypervisor for sure. Yeah. Which slide?
Okay, just stop. Can you please go to the previous slide?
This one?
Yeah. So, yeah, I'm a little bit confused. What are the benefits of all these like 8 virtual machines or so? Why are we overutilizing the VM? Like, why is this like 8 virtual machines instead of like 8 processes, for example?
8 process, yeah. So good question. Because of isolation. So let's say you don't have the hypervisor, okay? You go with the bare metal. When I say bare metal, that means you have only, let's say Ubuntu. And then you can run 8 containers. That's what your question is, correct? Because instead of using VMs, can I have like just Ubuntu, maybe real time, and then run the containers? Is that what?
But even without a hypervisor and with standard preempt-RT Linux, we can still have 8 container C groups
Agree.
and then prioritize them. So I'm just, yeah, this picture is just confusing me a little bit. I'm not saying it's wrong or I'm just...
Yeah, I'll explain you that one.
Yeah.
So the question is good. So see, even we have those use cases. So the use cases where your cycle time and the jitter are strict. Let's say you have a jitter requirement of 20 microsecond. Okay. Now the challenge with the one what you are saying, CPU pinning or the priority pinning, correct? You have the process and you can do the priority pinning for those. Let's say I have the 8 processes, I am going to pin those, correct? Now what is happening here is we have validated all those use cases. So the challenge with that is when you want to bring the system with the jitter, that defined jitter, most of the time with that mechanism, you will find more jitter. Now what is happening in this case is, you know exactly what your task and how much CPU time it needs, correct? So isolating each core, now even though some noisy stuff is going on my core 1, that noisy stuff is not going to impact something happening in a core 2.
But you are saying more jitter even though there is a separate kernel on each core. So I don't understand why there would be more jitter when there are a hypervisor and 8 pro
No.
and
So are you? I thought you were asking me without hypervisor.
You have 8 cores.
Yeah.
And each core has 1 hypervisor.
Yeah.
Okay, go on.
No, hypervisor is hypervisor is okay. So type 1 hypervisor and type 2 hypervisor. Everyone use KVM, I'm assuming. Okay. Now KVM is on the host OS. So you have a host OS, Ubuntu, and then the KVM runs on the top of that, and then you span your VMs on the top of that. That's your type 2 hypervisor. In type 1 hypervisor, basically there is no host OS. Each VM runs as if it is running on the bare metal hardware. So the beauty of type 1 hypervisor is it slices the hardware. Okay. Now that's why I showed you this service VM. Now what is happening is for all your housekeeping tasks, it comes in your service VM, and now you are literally slicing those resources with the type 1 hypervisor. So as if you are running on an independent hardware. So the requirement why we are doing this is because most of our customers have independent hardware, the way I said, fixed function devices. The factory has a fixed function devices. If I don't do this, they have the 10 devices doing that task. What we are trying to do is bring this in a consolidated way, but give the same experience that they have before bringing on this one, whatever their workload was.
Okay.
So maybe I think the clarity is more on the type 1 hypervisor. So type 1 hypervisor will work a little different. Type 2 hypervisor is what you are thinking. So type 1 slices literally. So this guy will feel as if it is running on independent hardware. It gets its dedicated resource.
Well, one quick question.
Yeah.
You have core 1, core 2, and so on. And what you do regarding caches? You partition them automatically with Archon, or how does it work?
So we have, I think you are touching the point which is very critical. You are talking about the cache, correct?
Yes, because if core 1 and core 2 share the same cache,
Uh-huh.
and the one monopolizes at some point, then core 2 is the victim and increase.
So there is not sure if you guys have heard about the cache allocation technology we call CAT.
So this is used by default.
Which one, the cache?
The CAT you just mentioned.
You can use PQOS basically. So we are going more into deep for each process. So I can talk a little bit on that one. So you're right. If you don't allocate the cache for each VM, then there is a challenge of eviction. But with the cache allocation technology, you can basically assign the cache to a specific core.
But who's doing the assignment? Is this Archon on its own, or
what is that?
The allocation? Who is performing it?
who is performing. So the way we deliver here, so when we deliver the hypervisor configuration, so we basically ask the developer, let's say in a 4 VM, they want to run the time critical task, okay, where they want low jitter. That's where you want to make sure that it gets the cache and you don't expect the cache eviction, correct? That's where you use the PQoS, where you do, again, it's kind of pinning, making sure that my process, my core, basically the virtual machine 2 needs the cache. So you can pin that cache. So there is the way I said core pinning, same way you can do cache pinning.
Doing it. You're asking who's doing it, right? In the software, you're doing it kind of static, right? It's sort of a
we
preset.
give a configuration, so it's kind of a drop. It's a configuration that we deliver via hypervisor. So it's a reference. So when we deliver to the end customer, so we give a reference saying that, okay, out of 7 VMs, maybe 2 VMs can do the cache pinning. Not everyone can do it. Cache is the limited one, correct?
Okay,
so
understood.
we deliver them the configuration, and based on their workload, they can decide where are they running their critical tasks. So they need that cache pinning there.
Okay, cool.
Yeah, the cache allocations, and where that should be done and more dynamically is a good question. But I think going back to the other one, I think the question he asked over there about why you need the hypervisor, I think you're using a type 1 because it gives you additional isolation for apps that have not been developed for preempt RT or specially developed. I think, is this correct? If someone could, what he said is correct. If you develop the apps carefully for preempt RT, you could do without a hypervisor, but the hypervisor gives you additional isolation and abstraction. And has some advantages there, right? So both are correct, right?
When I say, both of you are correct. But when I said why I'm saying we need this, when you have a strict requirement for the jitter, you want to make sure that you have the cycle time of 20 microseconds versus maybe 1 millisecond. So that's where you want to make sure that you get the more isolation. Versus when you are talking about, let's say you have 8 processes or 8 containers running, you can still pin the cores. In the containers can also be pinned to the specific core. So we are not against the container technology. That's why, but this was a very specific use case that our customer was asking. But we have another configuration where you can run without hypervisor, then you don't need hypervisor. You can bring in the RT and then you can pin your containers to the specific core. Okay.
Both are valid.
Good discussion. Okay, I think this was the second use case what I was telling. In addition to that, independent RTs, like multiple RTs and consolidating, we call more like a high density VMs. So you are basically squeezing more VMs on that core and utilizing all the 8 cores. Another use case, the way I said, like HMI, I've visited multiple factories, so I have seen they still have traditional ways. Their HMI is running on a separate PC. They have RT workload running on separate PC. So this is the use case where we are trying to do more like a workload consolidation is the one theme. And second is it has to be software defined. So when you bring in the hypervisor, that's where even you can deploy your VM dynamically. It's not like it has to be static, correct? That's where you bring the orchestration technologies, the way you are deploying the containers. Now you can even deploy the VMs. So as long as you have the support for the KubeVirt, let's say. So KubeVirt can help you to deploy in the VMs. As of now, we have very minimal support on the Acon for the VM orchestration, but KVM supports fully. So you can even orchestrate the VMs. So this basically helps you on dynamically orchestrating your VMs. So this is the use case 1. Again, can be extended. We have like CNC workload running here. So this is very specific RT workload. And then you have non-RT and HMI running in the second one. Service OS, we have to keep 1 core for a service OS. That's where most of the housekeeping task runs. We do have like a kind of pass-throughs available for most of our like IOs and all. That's where we use VirtIO. Don't want to go much detail, but this is another architecture. This one is more on the configuration. So want to show you like, okay, what was the configuration used for this use case? So if you are interested, maybe the Xeon D, we call Ice Lake D internally. So that was the one what was used, and most of the information is here. Software side, I think I spoke. One is we took stock standard Ubuntu as a service OS. We didn't patch that one. So the Ubuntu is used as a service OS. We just took non-RT Ubuntu. Then we had the Acon. Now Acon needs specific changes onto the kernel, so we had to apply those are the out of tree patches what I was mentioning. So Acon is, the Acon patches are not yet upstreamed, so we still have to carry those. So Acon was used, and finally the specific kernel that we modified, because of the Acon and other use cases, we had to apply those patches. So that's the combination. And what are the kernel configuration that we have used? All the details are there in the documentation. You guys can visit this website, eci.intel.com, and then the kernel command line options that we are using. So this is kind of just a configuration that we use for the tuning. Now, the biggest challenge is once we have that one core assigned, one RT assigned for one core, our job was to basically make sure that we are optimizing that, correct? So we had, what we did, maybe you guys can give some suggestions here. We ran the stress ng just to simulate the noisy neighbor, and then the iperf to generate the network traffic. So stress ng and network iperf are more for the kind of noisy neighbor, simulating the task. Then we ran the ftrace, and then the workload, to simulate the workload, we had the cyclic test. So we ran cyclic test to simulate the workload, stress ng and the iperf more for the network and the noisy neighbor. And then jitter is what we were focusing on. Okay, what is my max jitter? So as long as I'm hitting, means I'm within that bracket of the max jitter, then we are exiting. We are saying, okay, these are the configurations you can work. And if it is not, then we go back and again try tuning. So this is, again, the flow that we tried. The challenges that we observed when you have housekeeping and the real time running on the one core now. So remember what I showed you in the first one. So if you see, this is the traditional one. Now what is happening is we are combining everything onto the one core now. So when we tried this, so we definitely faced multiple challenges. So one of that was the soft IRQ. Soft IRQ was causing quite a number of milliseconds, in a millisecond the jitter. So soft IRQ was one issue. This IGB driver was causing another kind of a jitter. And then watchdog, basically it is connected with the watchdog issue. We had a patch for that. And then let's say you have a link, you have a network, you do net up and down. So that is, it takes time to restart. That was another issue for the adding the jitter. And finally the DHCP. So these are kind of our findings while tuning that RT. We came across these challenges, and I think this is what I mentioned here. So real-time task, housekeeping, they are running on the same CPU. That was a challenge. Soft IRQ was another issue. RCU, net driver was another issue which introduced the jitter, and then DHCP. There are some things that we thought, okay, we can optimize or update that. So the proposal is more on like use the hard interrupts instead of the soft IRQs. Instead of DHCP, the proposal is used more like a static IPs. And then some more optimizations around that preempted RT, stop some of the services. Again, now as everything is running on the one core, so do we really need those spin locks and basically the critical blocks, correct? So again, this is another basically thought to see if we need that one. Yeah, sure.
One thing, what's the issue with DHCP? I mean, if you offload everything to one CPU, including RCU, that shouldn't be an issue at all.
So I think if you see, I don't see if you can see the actual log. So DHCP was definitely adding the jitter. So instead of, that's why we are saying, okay, instead of that.
But it's a housekeeping CPU, so why do you care about jitter?
So now housekeeping is also happening on the same core. So it's a one core now. So this DHCP is also happening on the one core, correct? So we consolidated the housekeeping and the RT into the one task. So that's why we wanted to basically get rid of the dynamic one. Instead of that, just go with the static IP.
Yeah, but you don't. One thing I would wonder about is you have a neat reschedule, and this goes for a while until something happens.
Mm-hmm.
But this isn't that much. It's like 7 micro.
Yeah. So. Yeah, this is still in progress. So for now we are saying, okay, instead of DHCP, because now you have housekeeping and the RT running on one core only. So DHCP was one of that which was causing the jitter. So the recommendation was, okay, can we use the static IPs?
So just a quick workaround, you disable it for a while.
That was a quick workaround to just see if we get the improved jitter.
Okay.
Yeah, those are the, for now I think these are the kind of things we modified, and I think call of action. This is one example. I think the one where we benchmark, I'll just finish this one. This is my last slide. So if whatever the 4 things that I showed, so if you don't do those optimizations, you will see the jitter around basically 106 microsecond versus when we applied those optimizations. So we have the average maybe like a 22 microsecond. That was kind of the jitter that we observed after tuning.
I'm just a little bit skeptical of the claiming or declaring that preempt RT on a single core is something that needs to be fixed, or that's something that's not usual. Of course, ISO CPUs is a valid industrial case, and I'm not denying that. But to claim that preempt RT on a single core is not working, or that's like some novel scenario, is honestly totally wrong, because most a lot of our customers has single core on preempt RT, and it's because a lot of the embedded customers, they still use single core to save cost and stuff. So it's all okay, but just the claim that preempt RT and single core is not compatible is...
No, I think I never use the word it is not compatible. What I'm saying is the jitter that we expect for our customer is not achievable. That's why we started tuning it. So we are not saying that it is not achievable. That's why we want to do, correct? So what we are saying is on the single core, the cycle time requirement or the jitter requirement that we have. So what we did on this is we took the Debian and we basically took the minimal Debian image, making sure that we don't keep the other unwanted software components. So I don't think we are claiming that it is not possible on RTVM, single core RT. What we are saying is how can we tune it more so I can get the reduced jitter and I can have improved cycle time.
It's just because if there is trouble in that case, then that would be actually a preempt RT bug. So if there are like really high latency, like 100 microsecond or something, then this just needs to be f-traced more and root caused and fixed as an RT bug. So
yeah.
What you're showing is simply what you found.
Yeah.
And some of those items in that list, I'm guessing, need to be root caused. I mean, I was going to ask about soft IRQ.
It's not a solution.
That shouldn't be a problem,
Yeah.
but it was. But so I don't think you're saying that it's not possible. You're saying this is one attempt at implementation.
Yeah.
But and there's lots of things to learn, but it's totally possible, as he says, right?
Yeah.
I think you guys are saying the same thing, right?
Yeah. So this was my last slide, and this is where I'm asking Ms. Call for help is, I think if there are BKCs available, I'm happy to basically see, explore, and what we tried was very specific use case for one of our China customer, energy customer. That's what they came up with, and we thought, okay, let's work on that. And other options are also possible, like I don't need to have RTVMs, single core, I can have containers. And we have those configurations. If you visit eci.intel.com, you will find that multiple configurations we are building. We have the Docker configurations where you have only just the bare metal OS, and then you run the Docker and they do CPU pinning for the containers. I think those were the points that I had. Is the time? Yeah, we have 5 minutes. If you guys have more questions, you have.
More than a question, maybe it's something, an approach to try would be instead of, okay, it's to try, right?
Yeah, sure.
So instead of trying to make a single core system where you have your real-time application and the housekeeping things on the same CPU, right? Instead of trying that, one could try to run the 2 VMs with isolated CPUs, right? Housekeeping and your first case, and then try to pin that the CPU where you run your workload of 2 VMs into the same CPU. So because if you have, for example, two two workloads that are periodic. For example, 10 milliseconds period. And if they run less than 50% of the time, each one, you can have these two real-time tasks into the same CPU. You just need to shift one from the other.
Understood. Yeah.
And then you could have like two isolated CPUs on the VM, avoiding all the problems, trying to avoid all the problems.
Yeah.
And then having the hypervisor figuring out run this and run that on different times. As you run, I think those small hypervisors, you can have like a timetable of when each vCPU runs, right? So you could run, okay, this vCPU runs on the first half of the millisecond, that one runs on the second half of the millisecond, and both CPUs will be isolated.
You're basically time slicing that same RT.
Yeah, time is
two
slicing.
RT onto the one.
Yes.
If they are not using the.
Yeah. And then you avoided the problem of having your housekeeping work on the same CPU of your. And you still have like two virtual machines into two CPUs.
Yeah.
Just splitting them. It's something to try.
That you can keep. I have.
Yeah, sorry.
One thing you could look into it is regarding your watchdog driver.
Yeah.
We've seen it a few times with different drivers in particular, where the drivers do multiple writes to the hardware, and they get cached by the PCI bus, and then they get flushed at some point when you do a read or something like that. And then the latency accumulates because the read forces the CPU to stall, flush all the writes to the hardware, wait for the input, and then the CPU waits for the time. So we have this kind of bugs.
There is one patch, I don't know, I haven't looked at that, but there is a patch these guys have created. Maybe you guys have the slides on the website. There's a link to the patch. I exactly don't know what was the fix. Again, the way I said correct, I'm not the developer for that specific patch. But they have done some work around.
But I could encourage your people to send patches upstream and maybe CC me if they need further input to get the changes upstream for the drivers.
Sure.
Cheers.
Yeah. Thank you. I'll talk to you offline. Okay, guys, that was my time. Thank you. Maybe give your email. Oh, sorry.
it works.
There. Otherwise, repeat the question.
Yep, check the Mac. It works. All right. Okay. So, okay. Yeah, good afternoon, everyone. I hope everybody had a good lunch and had a good break. So, let me introduce myself a little bit. My name is Xu Huang. I'm a performance engineer from the performance team, the infrastructure group for ARM. So at ARM, I'm mainly working on performance analysis on post and pre-silicon for the ARM server cores, which is Neoverse, if you have heard it. So before that, I was doing my PhD from Texas A&M and working on program verification, especially for concurrency. And there are two other names listed here. They are my colleagues, Alokik and Malaj. Alokik is a director for the 5G solutions at the performance team. So if you are interested in building the 5G stacks based on ARM platforms, so he's a good candidate to reach out. And then Malaj is my manager, and who is responsible for the software development at the performance team. So in this talk, there will be less technology comparing to the earlier session in the morning. So I will mainly showing the performance data on our ARM server cores, which is Ampere. And also I will present a showcase showing how we find out the root cause of a large latency when we test the cyclic test on the Ampere cores. All right. So here's the agenda. Yeah, I will first talk about the background and the motivation for this work, so why the real-time kernel is needed on ARM. And then I will show some latency data on the Ampere Ultra cores. And then I will show you the issue we got, the large latency we observed during our test, and how we use the trace CMD to find out the root cause. Because I didn't know the real-time analysis tool before. Yeah, and thanks for the introduction, so I got some knowledge. Okay, so here's the background of why we did this work and why the RT latency matters for ARM. So the short answer is our customers ask about this. We have got a lot of requests from our partners, and basically the infrastructure performance team is mainly driven by the requests from for our partners like Google, Amazon, Microsoft, and those big cloud players. So ARM is getting more and more attention in the 5G space, especially in the past few years. So the left picture shows a 5G demo based on ARM platforms, which is presented at the MWC, the past WMC this year, the Mobile World Conference. So we are reached out by a lot of partners like NVIDIA and Microsoft and Wind River to ask about the latency issues on the ARM cores. Even though that they're running their own kernels or operating systems, like Wind River, they run the Starlinks. And for Microsoft, they run the Mariner. But even that, the root cause for the high latency should be similar. We share our tuning options, and some of them work for them very well. So that's basically the motivation for why. So the team is investing time on this. Hope this is big enough for you to read. Yes, this slide shows some latency requirements for the 5G applications, which is the slide is from my colleague, and it's basically from the link here. It is some specification or standards for the 5G applications. So here are some the latency requirements. They have very strict latency requirements. For example, for the AR, VR applications, the end-to-end latency should not be over 10 microseconds. And for some cloud gaming, should be under 7 microseconds, and so on for energy, power grid, some other applications. So the end-to-end is just from one endpoint device. The latency for end-to-end is from one end device to another end device via some radio access network. So there's something called the O-RAN. But I'm not an expert on 5G. So my job is just tuning the kernel and to make the latency as low as possible. So it's basically for some marketing purpose. So this slide is also some background information, and this defines how they how does the slide compute the end-to-end latency? It basically like for example, for an end-to-end latency based on the OSI 7-layer model, it is from the one endpoint to another endpoint. So here is like T7 minus T1. So this is end-to-end latency they define for two devices. And this is the latency like you got on the network traffic. You go through those layers and to reach via the radio station and then get to another device. But you also have some, you could also get some delay from the execution of your application in the operating system. So here's why like the RT real-time kernel matters for ARM. So there's some benefits like for the real-time kernel. So it gives you a it gives you a guarantee on how long that the application will wait in the for the CPU. And in summary, there are 3 benefits from the real-time kernel. One is like it can makes your execution quicker and it gives you a faster response time. And more importantly, for these 5G applications, they have very strict requirement on the URLC, so it's called the ultra reliable low latency communication. So it has some reliability requirements. Yeah, okay. I think I just talked too much about this some very obvious modifications. I think you guys are experts. You know much more about the real-time kernel than me. And okay, so that's the Next, I will show you the latency data on our ARM cores. And here's the OS information, the hardware information. We installed the real-time kernel from Ubuntu. So the kernel version is 5.15, and we didn't build or make any changes to the kernel. Just use what we installed from this link. And for the hardware, so our job is mainly focused on ARM cores, but here I also list a Intel core for a comparison. But we didn't do any tunings for the Intel platform. We just show you, when you see the data on Intel, it's just some out-of-the-box settings. So for the ARM cores, we use the Ampere Ultra, which has 80 physics cores. And if you do some tests before on this, so this is NeoVerse N1 based. It's our very beginning NeoVerse product. Now we have N2, V1, and V2, which are more powerful cores. But here you may ask why we didn't try any other server cores. So again, this is not what I decided because currently the partners are building 5G solutions on the Ampere cores, which is N1. And for Intel, in comparison, we tested on the Cascade Lake, which has 24 physics cores, and each core has 2 simultaneous threads. So in total, it has 48 virtual threads. So the Cascade Lake is the second Xeon generation of Intel server cores. And for the cyclic test, this is the benchmark we use to measure the latency. So the version is v2.20. Okay, maybe I just skip this because the introduction to cyclic test has been talked about many times in the morning. But I just quickly go through. So cyclic test is a benchmark that I use to measure the latency. So what exactly it measures is it measures the difference between you make a thread to sleep and you measure the intended wake up time and the time at which it actually is woken up. So this code is the measure logic for this benchmark. And on the right side, it shows a diagram how to make it more clear to understand how it works. So you have your task with RT thread, and you make it go to sleep, and then you wake it up, and then you schedule back. So the latency mainly comes from 2 sides. One is the
for the latency on the interrupt, and the second part is the latency on the schedule. So at the end, you just calculate the difference between the, so you use the n minus start and minus 200 microseconds. So I think everybody's clear about how what a cyclic test is and how it works. These are the options, the testing options we used for running cyclic test. So it's very standard. I just got this command line from the documentation of cyclic test. So the priority, we set it as 90, and an interval for 200 microseconds. And for the loop iterations, it's 100 million. So in total, the execution runs about 6 hours. Suggested by the documentation of cyclic test, it should be run a little bit longer for real-time testing. I think it's for some reliability guarantees. So for here, I just show you how we run it on a 64 cores, but we have tried some different core counts. Later, I will show you the data. And so, everything is here is very straightforward, and except the last one is you can bind the main thread on a specific core. That's for newer versions. I found there's no issues for older version of cyclic test. If you use a newer version, you didn't set the main thread, you will find that there's one core has a obvious higher latency than other cores because it runs the main thread on that core. So for newer versions, it's better to set this main thread on a gatekeeper. Okay, these are the options that okay, here's the histogram we collected on the ARM cores and the Intel Cascade Lake. So for the two pictures on the left side, they are the latency data for 80 cores and 24 cores on Ampere Airtrail respectively. So the y-axis is the number of samples. So in total is 100 million. And the x-axis is the latency in microseconds. So you can see that it has a long latency at the training of the histogram. And there's one purple line that is where it has a higher latency than other cores. I'll show you why this happens and how we fix this. Yes.
Quick question. Did you have any load on the machines while testing,
No.
or was it idle?
Sorry. Maybe I should make it clear. So in this talk, I didn't show any data with CPU load was CPU stressed. It's just the system is idle and run the cyclic test. We did some tests, so it gets the latency higher, but maybe that should be a fair comparison with CPU load. But for some marketing purpose, we just need to show the best performance number. So in this talk, there's no CPU load. Yep. Okay, so on the right side, so I think Intel did a pretty good job. So the latency, the max latency is just 31 microseconds. So don't get confused by these diagrams here. Even though the latency on ARM shows over 200 microseconds, but there are just very few samples that has a high latency. I would say for more than 98 or 99%, the latency is just 2 microseconds. It's just the worst case, but a very few sample like a single digit. Yes.
You mentioned Intel did a very good job. Are you sure that this is a CPU issue, not a Linux issue?
I don't think this is a hardware issue. It's more like because according to my experiments, I will show later. So we apply tuning options, and we can catch up the performance of on Intel. So
just that statement, Intel did a good job. quote my.
Good job. Yeah, I don't want to advertise for Intel here because I'm from ARM, so don't get me wrong. I just yeah, really want to show like ARM also like the hardware is powerful enough. I think because Intel has been developing these server cores for dozens of years. They have like did a very good job. I have to admit that they really did a good job on software optimization on the kernel and the software. So we have to face it. Yeah, I just want to be fair. Okay, so this is some initial like bug reports we submitted to Ubuntu. So these are some relatively easier to find out. So once is the RCU stores. We find this issue when we run the cyclic test with on 2 sockets of the Ampere machine. But on a single socket, there's no such issues, and they fixed that issue. And the purple line that I mentioned earlier, there's one core that always suffer from higher latency than other cores is caused by the CPP-C FIE issue. So this one has already fixed in the kernel. So the FIE issue, it gives some extra overhead from 2% to 10% on the CPU, even the system is idle. So the FIE is related to something like frequency scaling feature.
One thing, is this upstream or is it out of tree Ubuntu thingy?
I don't think this is upstream. We just wait. Oh, I think it's so. There's 2 links here. So the one link was to the bug report to Ubuntu, and the other link was a patch submitted by our kernel engineer Jeremy Linton. I think he's working on upstream. So he already found this issue, and maybe I didn't double check that. I think he's already submitted the patch to the upstream.
But at FII thing you said it is CPU frequency related, right?
Yes.
Yeah, so in general the device is not used at all. Just clock it to the highest frequency and leave it alone. You're supposed to have a workload where you don't need to change the frequency at all. Because if you lower the frequency, the core goes idle until the core is stable enough at the lower frequency. And if it runs at a lower frequency, it's slower.
Mm-hmm.
So there's like 2 reasons why not touch it at all.
I'm not very clear about your question. So
my point is RT-wise, CPU frequency, clock it to the highest one, and make sure you don't change anything at all.
Yes.
Then it's most likely what you did by disable FII.
Yeah.
So this is like...
It should be, that should be disabled, yes. Yeah. So, but somehow this one just enabled when we running the RT kernel, so it should be disabled. Yeah, you are right. So when you test the RT latency, so all the CPU should be run at the highest frequency. Okay, so after it gets more clear for the histogram. So the latency, the max latency just lowers to like 20 microseconds. But this is still not enough because our target is 10 microseconds for the max latency. And these are the tuning options that we added to the kernel to improve the latency. I don't think there's anything special here. All these options are either from the Red Hat, the online documentation. Yeah, you did a good job, I have to admit. And also some documentation from the Ubuntu and some other online resources. So yeah, I feel like everybody did similar things. The principle is just disable the time ticker and make the RCU with no callbacks, and also isolate the cores. I highlighted here which are the options most helpful for the latency.
Just editing. Yeah, probably all those things are in the Red Hat documentations, but there is also a tool named the Tundi that applies those setups here. It works fine, apart from that grumpy guy. You see, that's the documentation about that.
mean, we actually used TuneD for one of our customers, and it worked really nice. So I can't say the customer name here.
The thing about TuneD is that it does a lot of things in the background. It's not documented what it does, why it does, things it does. And for that reason, I don't like it at all. Like, it does a lot of things in the background.
Read the code. I'm joking. No, I see.
Yeah. So, yeah, there is pretty long verbose documentation, I have to say. Some of them work, but some just don't work for Ubuntu. So, yeah, the most useful one I just highlighted, just isolate the cores for running the RT threads, and also isolate the interrupts. So I just, for this test, I only assigned core 0 and core 1 for the gatekeeper. So this can fine tuning to find the best combination, but for me, I increased the number of for more cores for the gatekeeper, just does not help for the latency. And also, I need to emphasize the last one. At the very beginning, we didn't know this one helps. We figured this out for a later investigation. I will show you later. So I will next show the performance data without this. So with the kernel stack offsite randomization is enabled. So the results coming later will with this one enabled. And some other options like turns off the throttling, and also to move the kernel work queues to the gatekeepers, and set the CPU performance governor to performance to make the cores running at the highest latency. And the last one is, so this one is from the Red Hat documentation. I found this one helps a little. Just disable the graphics console, and I think, yeah, for me, it lowers the max latency like 1 microsecond, I feel. So I just put it there. Yes.
So basically, you are running RT tasks from core 2 to core 79. How are you dispatching the RT tasks? Are you dynamically dispatching them or statically allocating? What's your story regarding task dispatching? Because this is a large number of CPUs.
They have to be.
I'm not talking about the parameters.
They have to be static because they are idle CPUs, so he has no load balancing.
Yeah, okay.
Move on, please.
Oh, okay.
Yeah, okay. But like the Kubernetes thing we did.
Yeah, I can maybe answer your questions offline. Okay, so these are the latency data with those tuned options applied on 24 cores, 48 cores, and 64 cores respectively. And you can see that on 24 cores, it is very good. The max latency is under 10 microseconds. And when the core counts increase, the max latency increase a little bit. It's over 10 microseconds, 12 microseconds, still acceptable. But when it comes to some higher core counts, like 64 cores, the latency is over 100 microseconds. So this is, I think this is just for totally for business, for marketing purpose. Even if you make a very perfect number with the cyclic test, you can now see the system is perfect with real world applications. But it is what it is. The goal is to make the max latency under 10 microseconds. But you may wondering why it's 10 microseconds. Because we heard from our partners that Intel did so we want to catch up with them. Yeah, so that's the case. But I didn't see the data. It's just from Rakuten. They are running the Rocky Linux. They're saying, hey, they got the max latency under 10 microseconds. So a lot of come to me, hey, can we do the same? So that's why we really spent a lot of time on figure out why there's a large latency when it runs on higher core counts. Okay, so that's what I mentioned when the prior slide with the data with this randomization, kernel stack randomization enabled. But when we disable this, you can find the max latency goes down even with high core counts. So the two diagrams on the bottom are the updated performance data. I'm not sure if the title is big enough for you to read. And so the max latency is 9 microseconds. And even for 64 cores, it's still like 9 microseconds with this kernel stack randomization disabled. So how we figure this out? So I will show you in the next few slides. So I want to, see, thanks for the documentation. So yeah, right ahead, you can see here. Yeah, okay. Okay, so these are the documentations and the materials that we refer to for the RT tuning. So for the rest of the talk, I will, is a showcase slide showing how we figure out the root cause of the large latency on high core counts, and we also our kernel engineer submit a patch to fix this issue. So as I mentioned before, when we run the cyclic test with the tune options on high core counts here, 64 cores, there's a higher latency at the training part of the histogram. So it's definitely over 10 microseconds. The max latency is over 100. And this issue is maybe because it's difficult for me, maybe it's easier for you kernel experts. So it is, I think the most challenging part is it is not like bad as it looks. So when you pull out the raw data of the latency, okay, you can find that. So on the right side, so this is on the core 60. So the first column shows the number of samples. So, the frequencies. Oh, my bad. The latencies from 0 to 30 microseconds. And on the right column, it shows the corresponding number of samples. So more than 99% of the samples has just latency of 2 microseconds. Very few have over 10 microseconds. So this makes it harder for us to capture the root cause, and also the monitoring tool does not work. So then we have to come to trace. That's what I search online. So yeah, I use the trace CMD to debugging this issue, and because I watched a video online by Steven from the EOSS last year. You can find, so I also put the link here. So he gave a demo, and she's showing how to find out the large latency with tracing using the tool trace CMD. So that's what I use to debug this issue. If I know earlier than your tool, I probably will try your tool. I will next time if I got a similar issue.
I gave a presentation at the same conference.
Oh, okay. Last year? Oh, nice.
You might have a cyclic test scheme inside RTLA using timerlat in the background to help with the backward compatibility. But once you start using RTLA, you just don't get back. Hopefully.
Okay, I'll go on. So this is the command that I use around trace CMD to gather the trace and decode the trace. So the blue part that I highlighted is just the regular command for the cyclic test, and just adding the breaking point for the tracing when it reaches the large latency. Because even though we care only 10 microseconds, because when I enable the tracing tool, there's overhead. So I just make it to 100 microseconds. But I still cannot make it too large, like 150. Otherwise, it will generate more tracing data. It will make it more difficult to decode. That's why I also asked Daniel in the morning. And
I mean, the challenge of doing tracing analysis for this kind of problems is to figuring out what to enable, right? And
Yes.
in this example
Yeah,
here, it's enabling all functions and
Yes.
all events.
Yes.
So it's a lot of, it's way more than what you need. And
Exactly,
then
yeah, yeah.
fine tune it takes time.
Yeah, that's a good point. So if you are,
One thing I wanted to add is, does it record everything?
I think so, yeah, because yeah.
That's the thing you don't want usually.
Okay.
What you want usually is to run the recording in the ring buffer for like an hour. And the ring buffer is only like the playback for the last 100 milliseconds or even less, or maybe a little bit more. But the function tracer enable it's a lot.
Oh, okay.
Or not a lot, like, as I said, 100 milliseconds.
Okay.
Right? And then if the issue hits, and cyclic test has an option for that, it stops the tracer.
Yeah.
So does it record all the time or just the last few seconds?
Trace command there is recording all the time.
Yes.
Yeah, so that's like the bad thing.
Okay, I didn't know. Yeah, that's a good point. So,
So
definitely.
start the tracer and then you have trace command extract, where you would just, after the tracer stopped, extract everything out of it.
Okay. So you mean that the trace assembly also has similar features like a ring buffer, like it will override once it's full. Oh, okay. Yeah, yeah. Good point. I will make a note here. I didn't know that, so it's kind of annoying at the beginning when I watched like there are several gigabytes data. I just take several hours. It hasn't finishing decoding the trace, and so that I got a problem like when I decoding using the trace CMD report. I have to figure out, do some simple computation to figure out which core on which core occurs this high latency. So in my case, is CPU is core 63. So I only decoded a trace on that CPU. Because I'm running 64 cores, if I decode all the trace data from all cores, it's just too slow to decode. So yeah, if there's a ring buffer, I can just maybe make it easier for decoding. Okay, so this is the command line for tracing, and this is what I got. Because I just traced everything, so there are just millions of lines in the trace. So I figured out, but fortunately I figured out that most of them are just recurring. For example, here. So this is the piece of event sequence that it repeat over and over again in the trace. So even though you for a non-expert or kernel expert, it is not difficult for me to guess what it means here. So it's just like doing some like make the thread go to sleep, and doing some context switch and scheduling work from the cyclic test thread to the idle task, and then it wakes up the cyclic test thread and switch schedule back. So in a normal case, with low latency, it just repeats the sequence like this, and then when the breakpoint got hit, so it is over 100 microseconds, it will stop the tracing, and this is the problem sequence. So as a contrast, I show the screenshot of the problematic trace on the right side. So as you can see that when the cyclic task scheduled to the idle task, and then you should switch back to the cyclic task, but then somehow it just switched to the idle task again. So that's the difference that I observed by comparing a good sequence and a bad sequence. But there's still like a little information I can get from the sequence, the event sequence. Then I printed the functions.
One thing, if you go back,
yep,
you see cyclic tests on SCAD switch has a D.
Yep.
Which means it got interrupted at some point, and it got blocked on the lock. And this is bad.
Okay.
So this is like a hint this should not happen for your RT task.
There is another point here is that the cyclic test is not being awakened by an interrupt. It's being awakened on another CPU because you are receiving the rescheduling interrupt. Yeah, and that's it. It's not being awakened in the timer. It's being awakened on another CPU, probably because of the D. Yeah. Yeah, and the wake up came from another CPU because you don't see the wake up here, you see the rescheduling interrupt. And this could also be, there is one problem with timers that they are not always pinned. It's something that Ana Maria was working, and at Red Hat we have a hack on the kernel that says that if it's a timer from a real-time priority task, they are forcibly pinned to the CPU. It's probably the timer is being awakened on it could be, not sure because of the D. It's confusing that D there. No, I see. There's this, but there's also, it could be also the case of the timer, that D could be misinterpreted because of the, that. I know where he's going to. Okay, let's see where he goes.
Yeah, you guys are experts. I think, you can just take me like if I know nothing about the kernel and about the, this real-time stuff. And so this is just a step-by-step how I diagnose the root cause and find out the issue. So, but for here, I still cannot find anything useful. I just see the difference on the events. Then I re-decode the trace by printing the functions with the events. So this is the function trace, the stack for a good latency, low latency. And in comparison, like I list the problematic function stack trace on the right side. So on the top of the diagrams, they are just totally exactly the same. And highlighted by the right box, this is the difference on the byte latency. So if you read the stack, you'll find that the problem gets from the get random. The get random, some U stuff, U32, and then it has a spin log, and then it goes to call something called the CRNG make state, which is to generate the entropy for the random number generation. So then the next thing is guys simpler for me. I just to understand what this function does and why it makes a difference here, I just search the kernel code and to figure out what this function does. So I look up for the CRNG make state function here is something called the charge of random number generation. So it actually has a different paths here. In a normal case, if the entropy is not hasn't run out of entropy, it will just go to the fast path. But if the entropy just runs out, and then it will go to the slow path. So then you have some spin log and some more delay there. So that is why the high latency happens on the CPU. So, yep. And I talked this to the kernel engineer. And so the reason that why this is not an issue on Intel, so this is from my colleague, because the ARM just used the get random U32 to provide the entropy for the system core for the stack offset randomization, but for on x86, it's just using the time step to get that whatever for the random generation. So, but there's based on my colleague, the kernel engineer, Jeremy Linton, and so there's some problem here because it creates some non-deterministic in the system call, and when the random generation needs to be regenerate it or reseed. And he also had hacked a patch to try to fix the issue to use a relatively cheaper, I think, to generate the random, I think for entropy. So then after I retested the kernel with the patch, and so even with the randomization kernel stack offset enabled, the max latency is still under 8 microseconds. It's 8 microseconds. It's definitely under 10 microseconds. So, yeah, that's the showcase for how we debug this large latency on the ARM cores. I guess that's all. I think I still have time for questions. And
so let me say this, that you did a good job basically on
Thank you.
finding all the bits together. And what I'm sorry for is that you had to go through all this pain to figure it out by yourself.
It should. I mean, this work should not go to me. Yeah, it's totally different field than my work. So yeah, but it's fun. I would say like debugging this is painful, but it's really interesting. Yeah.
So I don't know why Ubuntu did this thing that they did with the RT kernel, but Debian did provide an RT kernel for several releases by now, and I have no idea what Ubuntu does different compared to Debian, but Debian does enables it and keeps it as a showcase. So you usually don't take this kernel and throw it on your RT workload that you have like a real workload, because you have a lot of things to tune left and right. Mm-hmm. So this is hardly the case. So you wouldn't usually have like this very long command line, because you would compile your kernel by yourself regularly because you have your own drivers and whatnot. Mm-hmm. And then you would most likely disable the things that you don't like. Yep. And one thing we could have, and we have this RT wiki where we provide or collect common configuration and steps and what to do.
Okay.
So maybe we could take some of these things and put it in one spot, and maybe Red Hat moves with us in that direction.
All of these command lines are also documented on the Red Hat tuning guide for real time, and it's open. But then we can copy and paste for the RT wiki. The Red Hat tuning guide for real time is open. It's not behind paywall anything.
Yeah, I don't mean we have to copy paste. We maybe could reroute those people. As long as you don't have this profile thingy, then it's all good.
So the last time I looked at the RT wiki, it says you should use no SMT. And no, I don't think you were using that. And then the other thing I'm curious, I don't know very much about how this...
SMT, you mean the multi-threading?
Yeah.
For ARM, we don't have SMT, but for, yes.
Okay, so that's not...
Yeah, for the Intel, we turn off the SMT.
Okay, and then I don't know very much about how the stack randomization works, but is the stack dynamically getting re-randomized and the entire system has one pool of entropy and it's getting exhausted more with more cores? Is that why more cores created a problem? Because the amount of entropy is sufficient for dynamic randomization with fewer cores?
There was a lock in the call. So more CPUs, more contention on that lock.
So I think what she asked is using the same like entropy, like when you have more cores, then you got faster to run out of the entropy.
Yeah, but there is also an RT spin lock. Yeah, so it could be that everybody is hitting that RT spin lock. So the more CPUs, more contention on the RT spin lock.
So what you have there is that you have a specific number of numbers within an array, which are pre-generated random numbers. And each time you need a random number, you just grab U32 from that array. And if that array runs out of numbers, then you need to reseed the numbers and generate more. And this takes time.
There's only one array for the whole system, is that right? There's only one array of random numbers for the whole system, and that's why more cores runs out of randomness.
I think they are per CPU, but point is you have more cores and more cores need to reseed at the same time. This is synchronized.
Regarding hyperthreads, it's not always necessary to disable hyperthreads on Intel. There are Intel CPUs that work fine with hyperthreads, and we are mostly using, we do this benchmark with the 10 microseconds. We use with hyperthreading enabled, they work fine. Most of them. Old CPUs had problems, now CPUs don't have it.
So my question, actually, before Sebastian interrupts me, regarding the CPUs, was not about the load balancing and how the scheduler assigns the tasks for that. I was asking, this looks like big server iron, big ARM server iron, right?
Mm-hmm.
So I was wondering, how are you dispatching the RT tasks at user space? So we had some customers, for example, who are using big iron, and we had to use some Kubernetes magic to load tasks at a certain way. So if you can speak about it, what is your picture on the user space side of things? Given the number of cores and so on, the high number of cores.
I'm not sure if this can answer your question. I basically understand what you mean. So we don't do some specifically like binding which core on run which workload, but we believe that this option, like this affinity to run the cyclic test on core 8 to core 71 and with the 64 threads, is that what you're looking for?
Yeah, that's part I understand, but I mean from a user space architecture side, how do you like dispatch your workloads?
So his question is, because you do isolate CPUs 8 to 71,
yes,
and you throw load on it, the scheduler never puts a task on CPU 8 to 71. So you have to manually assign a task to one of these CPUs in that area, right?
Yep.
And his question is, how do you manage these assignments?
Okay. Oh, yeah. I didn't pay. Yeah, I didn't pay much attention on this. I thought that cyclic test just automatically bind.
I think I can answer him. He's doing an experiment that is a standard for the people doing 5G. So the people doing 5G, they have this. They would like to have a CPU isolated, and they try to achieve this 10 microseconds because that's how the competitors compete. If they can reach the 10 microseconds, it's good. If it otherwise, no. But the people that will run the workload here, he's not trying that. He's just running the benchmark to see if it's good or bad.
Yep.
And then the people that run this tool is generally people doing NFV, Network Function Virtualization, and DPDK. They run busy loop tasks, and they are aware of affinity.
Yeah, I'm not sure task set is related to this. We usually, like, you want to bind your workload to specific cores, you can, but but how you can guarantee that the CPU load those workloads evenly, balancely, but for that question, I have no answer for that.
He wasn't trying that.
Yeah.
One thing, you run no hertz full as far as I've seen. If you will do for periodic, you could have lower latencies, but then for no hertz full, the latency is lower if you remain in user land all the time, right?
Yeah, but probably he's using that option because people on the field of 5G use that option because the people on the DPDK network function virtualization have the tools that only run in user space.
That's fine.
Yeah. That's the people that will run on top of this setup needs no hertz full because it's just a busy loop in user space collecting data from network.
Okay.
Yeah.
Yeah, I think we're running out of time.
That's why Rocky Linux works fine.
Yeah, thanks for your input and a really good discussion. And also, ARM is very actively working on collaborating with partners. So if you have any interest in running your workload on ARM cores, but don't hesitate to reach out to us. So we're really interested in looking at that. And also, I really feel ARM should hire your guys. Yeah, thank you. Thanks for your input and help. Thank you. Yeah, thank you. Yeah,
No, that's
thank you.
interesting. So it was in the same day after the talk.
Okay. Oh, I don't want to bring them back.
Oh, okay, I see.
Hello? Yeah, it's okay. Hello?
I'll make it louder.
Hello? It's okay now? Thank you. Okay, I think we could start. Good afternoon, everyone. My name is Jun Xiaochang. I'm very glad to have this opportunity to speak with you, speak to you today. I'd like to share my idea on this topic, tuning RT kernel to improve real-time schedule performance with the Intel platform. This is here a short description of RT kernel schedule performance. Firstly, thread could be scheduled at its expected time. Secondly, it should be low latency. Lastly, it should support a consistent response time. For RT kernel in this session, it's based on upstream kernel. And most of RT kernel patch has been upstreamed, but still around 100 out-of-tree patches. These kernels are maintained in below 2 repositories. The first one is RT stable. RT stable is for long-term kernel. Second one is for the mainline kernel. For prim-RT kernel option, configure preemptive RT. I think all of you here are Linux expert and should know this option well, but I still mention it here because it's a basic and the most important kernel option. It must be enabled, or else it doesn't make sense to select the RT kernel. By the way, this kernel option's name is a different. I mean, before 5.4, its name is configure preempt RT4. Here is the beginning. Which domains are tuned or improved for RT performance? The first is power management domain. Second is CPU cross isolation. The third one is timer and clock. Last one is debugging and lock detection related options. This page is about make tuning on DVFS CPU frequency in power management domain. If DVFS is enabled, sometimes the CPU frequency is high, sometimes it's low. For most of Intel CPU, if we disable CPU frequency driver, they will run in maximum and consistent CPU frequency. So for our RT kernel thread, sorry, not only kernel, for RT thread could be run in consistent and best performance, we'd better to disable CPU frequency driver. Currently, usually, there are two CPU frequency drivers for Intel CPU. One is the traditional ACPI CPU frequency driver. The second one is Intel P-State. We should disable them together. ACPI CPU frequency driver could be disabled by this kernel option configure x86 ACPI CPU frequency. The Intel P-State could be just disabled by just append a command line. Intel P-State equal disable. We could make tunings on CPU idle as well. Most of modern CPU support Intel, sorry, not Intel, idle state. When there is no thread running, it could enter idle thread, idle state. Intel CPU support idle state, idle C state, C1, C1E, C2, and so on. Bigger numbers means deeper sleep state. It could save more current drain, but it needs a longer time to wake up. These CPU idle related command line parameters could be tuned, adjusted for better performance. The first one is idle equal pole. CPU hardware idle will be disabled because the CPU idle thread is in a loop. It doesn't enter hardware idle state. By this way, its performance is the best. Its response time is best, but it couldn't save current drain. The second parameter is the Intel idle maximum C state equal a number. By this option, it could go to hardware idle state, for example, C1, C1E. The X number is a limitation for the maximum Intel idle state. The third one is processor idle maximum state. This parameter is similar with the previous one. The difference is this one is for the ACPI idle driver. The first one is for Intel idle driver. Usually, by default, Intel idle driver is a default idle driver. If CPU idle is enabled, I mean hardware idle state is enabled, we should enable S0X support in BIOS if the read. Traditional deep sleep mode support is S3, but if the read S0X support, we should enable this option. The read trade-off here, if we disable hardware idle state, it could get best performance. But if your device is battery powered, the battery will be run out of battery soon. So it depends on your real use case. If you enable hardware idle state, it still could meet the requirement. Then set a second parameter and disable first one. I mean don't append the first parameter and append the second parameters and set the number to maximum number, which the performance still could meet your requirement. This is better over. But if, for example, if your device is not battery powered, if you have an external power supply and the real-time performance is very important. It's much more important than battery life. So append the first parameter, I mean idle equal pool to the command line parameter. This the Intel idle state will be disabled, and its performance is the best. This page is CPU cooling. CPU cooling could be tuned for RT performance as well. Usually we might often ignore it. CPU overheating happens sometimes if the CPU is very busy. Then it might reduce the frequency to prevent overheating and hardware damage. To avoid jitter due to CPU frequency change, it is better to avoid CPU overheating, improve airflow for the device, clean CPU fan, and make sure it works well. This is important, but maybe we often ignore this. If there is a CPU fan related setting in BIOS, set it to cooling mode. Usually, if there is this option, there is, for example, quiet standard cooling mode, set it to cooling. You may hear some noise from the CPU fan, but it makes the CPU frequency performance better. This is for the Intel graphic driver tuning. If real-time thread needs graphic support, for example, if there is OpenGL, OpenCL calculation, or it needs a hardware video decoder, or it has some 3D application running, i9-15 parameter could be adjusted for better performance. i9-15 is Intel in Linux graphic driver name. First, the i9-15 command line parameter is i9-15 disable power wire. From the name, we could know it's just a power is always on. We set it to 0, means the display module power is always on. The second i9-15 command line parameter is i9-15.enable DC. DC means display C state. It's very similar with the one we just mentioned in Intel idle. Intel idle has a CPU core C state. For here, it's a display module C state. We could set it to 0. If we set to 0, display C state is disabled. Last parameter is i9-15 RC6. Sorry, this is not a command line parameter. It's a sys interface. We could disable RC6 if there is this interface. By disable this interface, Intel GPU doesn't go into, deep sleep mode. The performance will be better. Of course, it needs a current drain.
One thing, are you aware of the Intel ME driver for the new generation GPUs?
XE you mentioned?
It's not E915, but the other driver that Intel contributed for the next gen.
Next gen is XE. It's not, for me, from my understanding, it's not stable yet. I ever tried the XE, the new driver, with or Adelic 12th generation CPU. It doesn't work well.
Okay. My question would be basically, you showed like 3 options what to do, like display always on and so on and so forth. My question would be if the other driver has the same tweaks to be required.
Good question. Frankly, some different hardware their parameter might be different. But if you set these 3 parameters together to disable, it could make sure the i915 driver, the power display hardware driver power should be always on, because some older driver might support RC6. Some drivers support the parameter. Just a second, I go to the previous slide. Some hardware i915 driver support enable DC. Some support the disable power well. I think my opinion is to disable these 3 together.
Right, because we do have those in the RT wiki for the i915 driver, just to point people that those things may need to be tweaked. So I'm just curious if we should add the same thing to the other driver for that is upcoming. You say it's not stable yet.
For other driver, for XE, I don't think it's stable. It don't have such a kind of parameter yet.
Okay. But it could be also needed, right? If it's the same thing.
I think this is a good question, but I don't try XE yet.
Okay. Thank you.
Maybe XE should have similar parameters. I will add a to-do list. Add an item in to-do list too.
Thank you.
In this page, we talk about CPU isolation for real-time thread. The core isolation idea is simple. It's just reserve a couple of cores, or it depends on your use case. For high priority task running only, isolated core looks like a VIP room. Real-time thread is high priority real-time thread is a VIP. CPU isolation needs a kernel option and a command line change. The kernel option is configure CPU isolation. It needs a command line parameter as well. The related command line parameter is CPU isolate. Not a CPU isolate CPU equal a CPU list. In this case, in my case, I set it to 2. That is, core 2 is isolated. The second option is IRQ affinity. Since the isolated core is a VIP, so the IRQ should be migrated to other cores. This could be done by several ways, but the simple way is just to append this command line parameter IRQ affinity equal a CPU number. This CPU number shows a non-isolated CPU. By this way, most of the interrupt could be migrated to this non-isolated CPU. not all the interrupt could be migrated to the non-isolated CPU. For example, IPI, local timer, and NMI, such kind of interrupt. But most of the device interrupt will be migrated to the parameter we specified. In some system, there is a IRQ balance, so it might migrate the IRQ back to isolated CPU. So if there is this service, please disable it firstly. The last option is RCU callback. RCU callback should be offloaded to other core for the isolated CPU. So since we are VIP, we don't handle the RCU callback. Sorry. Hybrid core. Intel introduced a new performance efficiency hybrid architecture with the 12th generation Idlic processor family. It's a performance core. I think it's a good performance, but need more power energy. But efficiency core save energy, but its performance is worse than the performance. Its performance, I mean, efficiency E core performance is worse than the P core. So if the real-time thread need a lot of calculation, or its various performance is very important, so we could isolate the P core performance core. Usually, performance core will be enumerated firstly, so just isolate the CPU core in a small number. For example, 2 or 3. This is for.
May I ask a question about the P cores and the E cores? What are the kernel interfaces that tell you like which core is P and which core is E? So.
Good question. For me, I don't know. Currently, it looks like there is no easy way to tell you it's a P core E, but the first core, the core in small number is a P core. The bigger number is a E core because E core are enumerated lastly.
Okay.
For example, if you have 4 P core, 4 E core, usually the first 8 core is a P core because it has 2 logical core. So then the last 4 core is E core.
Oh, okay. Oh.
Hi. Could you maybe read the E or P core from the CPU ID string?
Yes, this way is okay. CPU ID could, there is a CPU ID instruction. You could read a CPU ID and then get it's a P core or E core. Yeah.
Yeah, also regarding these E and P cores, how are they enumerated in the CPU list? So is it always the last ones are the E cores, or is there no special meaning behind the number?
For my understanding, usually P core are enumerated firstly. So if you cat the CPU info, the CPU ID number which is small usually is P core. I don't know how, I didn't pay attention on this, how they are enumerated, but usually for my understanding, the small core ID, the core ID which is small, they are P core. I think they are good question because I think we should have a proper interface to show kind of core is P core or E core, but currently there is no. This is for cache sharing. This is very important, but usually maybe we ignore it as well. Cache performance of high priority might be impacted by low priority, which is enable logical core. For example, if you have a real-time thread, high priority thread, and for example, you are running a real-time thread, you control robot arm in core in this page, logical core 2. In the same time, there is a low priority task which just saves the offline log to the file system. It's a really low priority. In the core logical core 3, then because logical core 2 and logical core 3 they share L1 and L2 cache, then your high priority task cache performance might be impacted by low priority task. Unfortunately, this is fortunately this could be avoided. In our testing, we often isolate neighbor core. And for example, logical core 2 and logical core 3, we isolate them together. By this way, high priority tasks will not be impacted by other threads. And the cache performance will be consistent. For how to get cache sharing and related information, I note here below, there is a sys file system interface. The path is a sys devices system, CPU number, cache index. This folder, it has all kinds of cache related information. For example, cache size, cache type, and cache sharing information. Pay attention, please share the CPU logical core together if they share L1, L2 cache.
Oh, sorry. Yeah, but isn't it recommended to disable SMT hyperthreading when you run the RT workloads? So then, will that avoid this cache sharing issue?
A good question. I think for multi-thread, not multi-thread, hyper-thread, for this, I don't recommend to disable at all. We could, I think we could just isolate two logic cores together. If you disable the hyper-thread, you will have less cores, right?
So I handled this question many times internally at Red Hat. The reason is that, yes, if you would like to try most of your latency, yes, it is a big hammer disabling hyperthreading, but you are losing half of your CPUs. So why do you want to lose half of your CPUs? What happened is recently Intel CPUs, they're getting the same number with or without hyperthreading. So yes, it's not a recommendation, it's try to see if it breaks things or not.
Of course, if your company is rich, you have enough budget, you could order a CPU or device with a lot of cores. You just disable. It's okay. Just kidding.
Yeah, but we also run into situations that when you enable SMT with the hyperthreading, you got actually worse performance. Mm-hmm. So we actually, inside ARM, they have like a lot of discussions why if we really need SMT or not, when we do comparison with the with Intel cores, should we enable SMT or disable SMT?
Yeah, actually, I'm from Siemens, and we had the same discussion also many times. The biggest problem is that you have shared resources within these SMT cores, and like the FPU. So if you really know your workload, then you can run both in parallel. But usually we don't do that. So we are better safe than sorry, and just disable the SMT for the real-time cores, and of course for the others we can leave it on.
One thing to consider is if you have one thread only and you run it 100%, and you have 2 threads instead fully loaded, then you run at roughly 70%, maybe more, maybe less, depending on the architecture. So this is also a performance issue, what you want to have. And if you disable them, you have consistent numbers. If you don't disable them and you have them, the numbers may vary. So it's depending on the use case.
Yeah.
Yeah, and that's about it. It's depending on the use case. It's not a rule. For example, people using the PDK on Intel, they run with hyperthreading enabled, and that's good enough for their performance. So the best performance is not always related with the best use for the platform.
Yeah, I agree with you. This is no clear answer. It's a yes or no. Sometimes it depends on your usage. But from my opinion, I prefer to isolate 2 neighbor cores together. By this way, we don't need to disable. We don't disable hyper-threading, but we still have a lot of. I think we still have enough cores. For this page is about a clock and a timer. Modern Intel CPU has multiple. Modern Intel CPU has multiple instances of a clock source. For example, TSC and HPET, legacy PIT or RTC. TSC is a register in each core. There is TSC read and TSC write instruction. Its performance is the best. So usually, by default, clock source, the source is TSC. By default, it's TSC. But append these 2 command line parameters to make sure to double confirm the clock source is TSC. The first is the clock source equal TSC. The second is TSC equal reliable, or TSC equal no watchdog. The first is make sure current clock source is TSC. The second is with this parameter, I mean TSC equal reliable. The kernel thinks the current TSC is stable enough. It will not kick off an extra timer, clock source timer for clock source calibration. The second is to try to make isolated core thickness. The first is to enable kernel option config no hertz full. The secondly, you need to append the command line parameter no hertz underscore full. This is to stop timer whenever possible. If there is no handler, there is less interrupt handler, the real-time performance should be better. The last option is timer migration. Even we isolate a CPU, sometimes the timer still be migrated back to, not migrate back, migrate in the isolated CPU. Before we do launch or real-time task, firstly we disable timer migration by echo 0 to this proc sys interface.
There's a few things I find it kind of difficult to suggest TSC reliable by default to everyone, because we have this watchdog for TSC because it's not always reliable.
Mm-hmm.
So if Intel guarantees for you SoC that this TSC is reliable, you usually have a CPU ID flag for it, which you can query. So this shouldn't be required. I'm aware that a few atoms don't have this, but Intel claims this is reliable, you can skip it. So this is different, but I wouldn't put it as a rule of thumb to just disable the watchdog and be good with it, right? You agree? Yeah, but
for my testing, I often open these two parameters because I often use maybe it's for example Taglic is 11th or Adlic 12th. Maybe the hardware is new, so this parameter is okay for my hardware. Yeah, for this hardware.
That's my point. If Intel says this is okay, and I'm aware of all the atoms where the TSC was okay, but it wasn't exposed by the CPU ID, and then if you override it to skip the watchdog, then this is fine. But I wouldn't give this as a rule of thumb, do this, you're safe. Because the TSC might not be safe, it might catch up during boot or later on. They might not be synchronized against other CPUs, which is figured out later on in the system. But with this, you disable all the checks basically.
I need to add a to-do list to check this.
No worries.
Good question.
One thing regarding no heads full, it usually makes sense if you rely in your application in userland all the time, and you have roughly no or little changes to kernel for whatever you do. Because if you have no heads full enabled and you have frequent changes to the kernel and back, then this is more expensive. You isolate it to your core 2, then this is okay. But this is more or less use case dependent, but yeah.
Okay, at least for the first reliable, for this parameter, I will add it to the list. I will try it later, and up to you. If there is a next EOSS session, I will explain it in next.
Just adding, probably most of these tunings that we are seeing here, they are biased by the case of the network function virtualization people trying to run busy loop tasks, and then that's the case of no hertz full, because they just keep in user space. So what we are seeing, it's normal. We are all trying to get the best number, but the best number depends on the application. It's then that's why it's all variable. Do I need it? Do I don't need it?
My idea is just to reduce the timer and other interrupt as many as possible. So I think the performance should be better.
Yeah, no, it's better, but at which cost, right? At which cost? So it depends on how much cost do you want to add the penalty. If you want to do the best, you might make a non-reliable choice. You might throw away half of your CPUs. Okay, you get the best number, but that might not be the best option overall, because you might better have all the hyper-threading. You better play safe with this. So there's always this trade-off, and I think that's what people, we are all in agreement here.
Yeah, a lot of trade-off.
Yeah, we are all in agreement that there's this option. We need, depends on the worst case, the use case.
Okay, let's move on.
And that's actually, for me, was one of the benefits of TuneD, because TuneD has a lot of profiles for different use cases like networking, virtualization, and others. And it actually helped me, whether I use it or not, was to help me actually see which actually which actually helped me to at least know which options are recommended for virtualization, which options are recommended for networking, which options are recommended for DPDK, which does most of the networking in user space and so on. So,
yeah.
I think we're talking a lot about tuning and different use cases. Before I go, I have a statement at the end, but how many more slides do you have? I want to make sure you get through your presentation.
We should.
How many slides do you have left?
Yeah. I think we are soon. It's around for 5 pages.
Okay, why don't you go through the 5, and then I think what I was going to say is I think this tuning topic is something that is dynamic and changing and different use cases. My main thing is I don't think any of us should look at any, and it was great, I think it's great that everybody's sharing, including the previous presentations and that. I think it's dynamic learning of the industry, and we shouldn't take any of these as too, there's not one size fits all, as you were saying, right? And we're learning, right? So that's the only point I wanted to make. So
Yeah, good. I just I didn't notice it's around 35 minutes. Okay, I will move on. Okay, thank you. This is a debug and locking detection, and disable all of debugging and related kernel options. For example, kernel debugging, key memory leak, slab debugging. Usually they are by default they are enabled. For example, in a lot of systems, for example, other kernel operations is related with debug KASN or UBSN, kernel address sanitizer, and undefined behavior sanitizer. By the way, these two sanitizers are very useful, powerful tool. We fixed several kernel bugs with these two kernel options. But they slow down the kernel running. So before you run cyclic test or other real-time thread, please disable these debug-related kernel options. For the kernel command line change, the no source lockup and nmi underscore dog equals 0. It means to disable extra lock detection related timer. With less timer, we will get a better performance. This is a trade-off as well. We get a better performance, but we lost a lot of debug-related features. So before we do the real-time thread tuning, first make sure our system is stable enough. So we could disable debug-related kernel option. This is our testing. The hardware is a NAC. Its CPU is a laptop CPU, and the software is Ubuntu 22.04. Kernel is upstream 6.6.20 RT25. Test tool is cyclic test. We set up two tests. One is before tuning. It's Ubuntu 22.04. Kernel is 6.6.20 RT25. Only change is the prim RT kernel option is enabled. The cyclic command is here, C1P99M-S. It run for one hour. After tuning is based on the first test case. It's enabled all the tuning and optimization which mentioned in this slide. During the cyclic running, we have run below workload in background. The first case is idle, no background workload, just run the cyclic test. Second case is run stress ng. It's launched for 8 threads, 4 for CPU, 4 for cache. Stress ng is run the background. Cyclic test is run the foreground in foreground. The third case is run IO stress in background. This test is just DD a big file to the local file system in an infinite loop. The last one is 3D testing, run GL Mark II in background, run cyclic test in foreground. These 4 test cases are run for both before tuning and after tuning. That is, the cyclic test run for 8 times. This is the test result. The before tuning, the color is in light blue. After tuning, the color is in orange. From the result after tuning, its performance is much better. This is reference for the first reference is Intel Core Processor Real-Time Tuning Guide. For this tuning guide, its CPU is for network and edge. Intel has not only CPU for laptop and server, but also has a CPU for industrial, medical, and telecommunications domains. Their CPUs are different. For this tuning guide, it's for the network and edge CPU. It has specific features such as cache location and TSN or TGPL related features. It's different with or desktop or laptop CPU. If you use a CPU for industrial, for medical, for communication, please ping our marketing. They will have much more detailed information for that. The second is just a blog for tuning a real-time kernel. It's pretty good. That's all. Any question? Okay.
Thanks. So one thing we always see in these real-time talks is the isol CPU parameter. But if you look at the kernel documentation, you will see that this is deprecated. And if you look at it at practice, if you combine that with the C group version 2 CPU set manager, it's fundamentally broken. And I'm really wondering if there is a good replacement for that, or why we always see that in the tuning talks.
There are some things in the kernel that are more of a message than a rule. For example, the RT is already merged. We have the option in the kernel, right? That's a message. It's a message that the parameter RT will be merged, right? The message on the deprecation of the isol CPU is a message saying, we need to get something better than this. We still need.
Don't we have it?
Yeah. Somehow it's not yet that confidence. People are empirically getting back to isol CPUs because they found a point here, a point there, a point here, a point there.
My question is, Wyman did some work on this C group thingy, and my understanding is that this replaces isol CPU completely, and you can reconfigure it at runtime best to your needs.
We use those things on OpenShift, and we get those numbers, right? But it doesn't work for everybody yet. So people fall back to isol CPUs. On OpenShift, we run these 10 microseconds latency tests. For NFV people, we have all these setups. That's why Tunity work. It's because of those things. And on OpenShift, we don't use isol CPUs because now we have a one use case here. Now it goes away, and there's another workload that doesn't depend on it. And so the setup is always changing. And we do this online and don't do. So the results are good, but sometimes it doesn't work for someone, and they fall back to isol CPUs because it works.
My point is isol CPU removes the scheduling, the CPUs from the scheduling, and this is mostly what it does, except for the timer goes away and all those kind of things. Yeah, I mentioned this one. However, what Wyman did, what I mentioned before, is that you can use C groups and you can use an isolated C group and do what isol CPU provides with C group features. And you can dynamically configure and remove the CPUs from this. Exactly. So this is mostly the same.
This is the scheduling part. So it removes I think it's root, turning it root. So yeah, it returns its root as the root of the root domain. So the C group is its root domain. So our root domain is outside of the other root domain. So the other root domain doesn't migrate its task there. That's why the task doesn't migrate. But that's not all, because there is all those setups on managed IRQ, dependence on the RCU that are still binded to the CPU mask provided by the isol CPUs. And many of these parameters, they are only acceptable after you reboot the system. And because it's not persistent by reboot, they still need to use it in the command line. We discussed this at the Plumbers last year. Frederick was working on something like this. And there are still parts of these full ISO CPUs that depends on things that we still require reboot. There is working on it. We even discussed things like, oh, okay, if you want to turn the CPU not isolated and isolated, one workaround would be instead of rebooting, you turn the CPU on and off. But this doesn't work because if you have like one CPU, if you run timer.lot on a CPU and you turn off the other CPU, the machinery for hot plug creates latency on the other CPU. So there is still work to be done to make it correctly. And that's why people fall back to ISO CPUs, because it depends on things on the.
So I don't want to hijack the session, but one problem here is really that when you run any container manager on your system that uses cgroup version 2, it will activate the cgroup controller, the CPU set controller, and by that it will reset some of the default affinities, and by that including the effect of the ISO CPUs. So there, it's definitely broken.
No, it's not, because the affinity is set to all CPUs, but the load balancer is still removed. Yes. So unless you change the mask to exclusive to the isolated CPUs, the scheduler never moves you over there. Yes. So this is just a trick question, but that doesn't affect you.
Creating a root domain is part of the isolation CPUs. It's not all. When you create, all the idea of isolating with C groups is creating a new root domain out of the other root domains that have the load balancing. That's part of the problem. It's not the entire problem.
If you do the ISO CPU thingy, and then the scheduler load balancing is removed from the domain via the command line. Yes, but it's removed, right? Now, if you do cgroup v2, then by default, every task has this task affinity set to the non-isolated CPUs, right? But with cgroup v2, the scheduling enabled, the mask gets reset once the controller is enabled. That's why he says it's broken that way. However, the CPU mask is set to all CPUs, but the load balancing is removed, which means the scheduler never pushes you there. Therefore, it's not really broken then. It just looks odd.
It just looks odd if you look at the affinity.
Yeah, exactly.
It looks odd because you look at the affinity and it seems that it will run there, but it will not run there because it's a different root domain. There's work to be done. But yes, but that's it. For now, the deprecation is more a message than a. If you see at the Plumbers last year, the scheduling micro conference, there is a talk from Frederick Weisbecker, and where there is this discussion on problems that we still depend on the ISO CPUs.
Okay.
Sorry for raging.
Thank you. Well, the last problem for the isolation, if we disable isolation, we don't put any isolation related command line parameters. The problem is still good, but less than the isolated CPUs in our testing.
If you isolated CPUs, you don't even need RT, because the CPU isolated, there's no task running there, there's nothing to be preempted, we don't need RT.
We could have logs in the kernel.
We could have, if the CPU isolation is done properly, no.
Depends on resources if you go to the kernel.
No, for the NFV case, where it's all user space.
The memory allocator, for instance.
The memory allocator. But it won't will it affect the current CPU or just the other CPUs?
Well, you have your per CPU slab allocator, and then if this is off, you go to the byte allocator, and this is like a Luma node based.
And if you have like a housekeeping CPU to run this part of the code there, you probably don't need RT.
It depends.
No, yeah, in most of the cases when you have a CPU isolated, you don't.
You might get out of it, but this
Yeah.
depends on your shared resources.
Yeah. But it's something for many people. Many people are running the ISO CPUs with RT, they don't need RT. But that's long discussion.
okay.
And that's the wrong audience, because I'm talking on behalf of RT, and then people punch me because I'm going against RT here. It's not always necessary, but long discussion. Yeah. Yeah, we need to keep friendship.
Yeah.
Yes. If so, that's all. Thank you. Thank you all of you again.
Of that, like which one got you the best
There's multiple over there.
Just before starting, we were planning to have Thomas here, but he had more than one problems with flights, and he's landing now. So he will not make it. And it's not in Seattle yet. So, yeah, we can always miss a deadline. This is not a hard conference, right? We are all kind here. We might have discussions, but only on LKML, right? What happens on LKML stays on LKML. Here we are all friends, often. So we tried to manage a Zoom call with Thomas. He was now finding a place at the airport, but unfortunately we would have to be in another room where they could capture the audio. It would be too hard. We tried our best. And but anyways, the idea here is that this is not, as I said at the beginning, the idea of this event is not to have like very leading edge discussions about what will happen in the kernel, but instead to build community, right? To get to know each other, to get to know the best practice, to point to things to the other, to learn with each other. So it's an easygoing event anyways. And the idea here is that we could chat. We would have Thomas here, but we have like, I work with the scheduling part on the real time, with tooling. We have Sebastian that maintains the Preempt RT. We have Kate that manages the community and tries to get people together. So I think we can, the idea is for us to sit down here and, okay, and think what we have been doing in the last years to make the push forward, what motivated us, right? And what we are doing as development for the near future. And we'll start talking here. And if you guys have any questions and would like to go deeper on any argument, just raise your hand, join the talk. This is just a chat among us as a community, right? Should we start?
Sure, let's start.
So maybe I will start with Kate.
Okay.
Hey, Kate, what is the motivation behind this event or the real-time community within the Linux Foundation? What motivates us?
Well, there was a problem out there, and there was a problem that a lot of people want to use Preempt RT and want to use real-time scheduling, and it was outside of the kernel for a long, long time. And so a variety of companies got together and said, okay, we'll help fund doing it properly, doing it right, doing it upstream. And so it's been about an 8-year journey at this point now. And I think we're pretty close, Sebastian, right?
Yeah.
Okay, good. That would be good.
We say this like year after year, but if you look for the patch queue, what we had like in 3.0, in 4.0, in 5.0, in 6.0, it's way less core code, and it's mostly drivers that are left over. And the only core code part we have is like the print K department. And other than that, we don't.
Is it almost done for print K?
So for 6.0, by the time Linux released it, it was said that there is nothing special. And I tried to sneak in RT into it because basically I was going to disable the printing to the console, and this is technically our only problem. So you would boot the system with RT enabled, you wouldn't see anything on the console, on nothing, but you could do dmask and see all the messages. And Linus saw this, and he was not really amused about it.
Oh.
I was about to ask you, what happened then?
Yeah. So then he asked us to just revert this, and then I was like, okay, then this is not going to happen now, and then we just have to move on.
Just keep going.
Yeah.
Okay. Well, you know, to the credit, I guess, we had enough of companies join in and help create and fund a pool so that we could actually have the work done properly and fund it. And, you know, this wouldn't have been possible without various members subscribing and helping it. And it wouldn't have been possible without you and Thomas's team working on it. And so, you know, over the years, we've had ARM, BMW, Ericsson, Google, Intel, IBM, National, NXP, And we've had some of the Red Hat, of course.
I was waiting for it.
Of course. We've had the EOSS group who started doing some of the real-time stuff earlier on, and they've been engaged. So it's Texas Instruments, and then some of the Linux Foundation projects like the civil infrastructure and the LISA projects have helped chip in to see if we could actually get this preempt RT upstream. And, you know, I think over this 8-year period, I think about 5.7 million or so has been raised to actually do this bit by bit. And so, you know, doing things upstream in the kernel, and doing them right and doing them over this period of time really does take an effort and a community to get behind it, even if it's not. And when we started it, we really didn't have like a whole team of stable maintainers maintaining the backports, and there's been a team that's been formed for doing that.
We
and
meet
all
every 2 weeks for that,
Yeah, well, you can tell us. You can tell them about what you guys are doing in that, because you're on that call all the time.
Yeah,
and so Sebastian, for that matter.
Yeah,
He's telling us what's
Sebastian.
happening there.
No, I'm more in the things around. I'm not working directly with preempt RT. I'm working more with the scheduling side and tooling side. Right, I'm more participating on that side of the meeting. The preempt RT bits it's more on Sebastian's side.
Right. I mean, we meet like every other Friday, and we discuss like if everyone has problems with things backporting, if there are things to be backported. And sometimes Greg picks up things that collide with the other releases because RT back then had something different. So then I look, or someone else says what needs to be done or what he did, so he proposed, and we check if this is what's supposed to be done. And sometimes we noticed after the release was done that something broke. And then when we decided to do RC kernels for the review on the list before doing the actual release, and I think this helped a lot.
Yeah, I think, you know, the fact that Red Hat and SUSE and all these other distros have stood up, you know, come to it and help keeping these backports going, because it's in their own interest to keep them going, mostly.
Yeah.
Right?
Yeah,
but it's a lot of work. It's a lot of work to keep backports going, so getting everything upstream is obviously going to help us, right?
Right.
Yeah.
Yeah, and after all these years working upstream, I get to the point of why it's not a good thing to cut corners on merging code. Right? For example, we have been working in the RT throttling problem for 5 years now, which is in the scheduling side. It's not on the preempt RT side. And many of the ideas that we had over the time, they would lock us in the future because we would be adding an option that we would regret. And we know that when we add an option that we regret in the future, we cannot take it anymore because people start depending on it. So cutting these corners on the upstream development, they doesn't help.
No.
So do we have something now for the RT throttling issue, or?
What is the throttling problem, right? We see many people here disabling the RT throttling as a setup, right? That's a pure sign that that thing is not working well. And the main problem, what is the idea of the throttling? Is that when you have like an RT task that doesn't behave, that runs like for a long time or forever, what happens? It could end up causing starvation on the non-real-time tasks that need to run on that CPU. And one would say, wow, but you can remove the task, but not...
Wait, the problem is basically that you look up the system without knowing what happens.
Yeah. If you disable the RT throttling, you lock up the system, because there might be some CFS work that end up on that CPU holding a lock.
Well, you don't see any console output, your SSH is dead, and you don't see what happened in the end. Right.
Yeah, for example, K workers that are per CPU and that might starve and holding a lock.
Exactly.
Right? So the throttling serves to avoid this starvation. The problem is that the current mechanism, it is not aware of what is running on the CFS. So by default, a busy loop real-time task, it runs for 95% of the time, and then the entire RQ is throttled, depending of what is going on the CFS, right? And this is bad because you can only run 95%. You would like to run 100% of the time, right? So instead of pursuing this idea of throttling the RT run queue, Peter came with the idea of instead of doing this, we should boost the CFS as a real-time task, right? And the way that we are doing it is we are encapsulating the CFS inside of a sched deadline reservation. So we reserve a piece of the scheduling time, like a runtime in a period, like a sched deadline task, but not to a task, to the entire CFS RQ. The problem with that initial approach was that because the deadline is higher priority than the FIFO scheduler, what would happen is that the CFS scheduler would run before the RT. And this will break everybody's here scenario. So now what we are working, then we have, just for you to have an idea of why things takes time. Then the first idea was writing a new scheduler just to schedule the CFS, right? But this would break the sched deadline. And then we started discussing the idea of deferring the activation of the deadline reservation of the CFS using the sched deadline. And that's the thing that we are pursuing now. And that's what makes hard, right? Because we need to add this option without breaking everybody else's workload here. And we are reaching there. It takes time, but we are reaching there. Adding as less options as possible to try to not regret in the future for the things that we did now. And that's why things upstream end up running slow but consistent. Yeah. It fits the PM30 case.
Yes. Okay. So are the device drivers going to be needing to be changed much?
I hope not.
That's the answer I was hoping to hear. What's the impact going to be once it's all upstream on the rest of the kernel? Is there anything that's going to have to go in and get changed before, or has everything been changed as part of doing it upstream, getting it all upstreamed?
I think it's part of getting everything upstream.
You think we're there?
I think that's, I mean, I have still a queue left, but this is like ARM, and there is not a lot of people asking for ARM right now, and posting patches to the ARM list tall, and I have like 0 replies, and like no one cares.
Oh, we can fix that.
But to give you another example, I sent patches towards ARM64.
Yeah.
And they look at it and they say, oh, we would like it a little bit different. And before I get to the point to react, they send already what they would like to merge.
Oh, they really want it fast.
Yeah, so you see, that's like the difference, like 100% the other direction.
Okay, so ARM64 is reacting and ARM32 it's not.
Right, and RISC-V came along and they presented like 4 patches. And then I pointed them what they need to do, and then we reduce it to 3. 1 which they merge, and 2 they have to keep, and this is like RISC-V.
Okay.
So they asked for it as well. So those are like the good ones.
Okay. Are there any architectures that are going to have problems and not have access to it?
So I remember the early days with 3.10 or 4.0. You had to do a lot of work to get the timers right, to get perf right, to get this and that, and kernel exit, and so on. But these days, we have most of the things generic. So if you look at RISC-V, which was a new architecture and used almost everything in a generic way that was supposed to happen, they had very, very little work to do.
Excellent.
And so for other architectures like MIPS, for instance, they would have to either go for the generic way or look what we did for the others to manage it.
And do the ports for their own architectures themselves.
Right.
If they want to keep working with it. Okay.
The good point is that the discussions now are just following the regular kernel development, right? They are not the PM30 as an isolated patch set working there first.
Right.
They're happening on the regular workflow, right?
But this is what I have the pleasure like to do these days. Like this is broken today for the interrupts. This is broken today with HR timers. This is broken into this and this assumption, and we have a document, and the code is already there. In the past, I pointed people to the tree, pointed out the problems, and no one really cared because it's yet another out of tree project. So this was really hard to work with. But we had like the tracing came out from the RT project. So it wasn't, we need tracing because of RT, like we could sell it, we need tracing because we don't have anything for the tracing thing. Yeah. And this was easy. And the more we got out of the RT tree mainline, the less people were interested to get actually the remaining RT bits because a lot of...
The benefits were already mostly in the kernel.
Right.
Yeah. Yeah, so just recalling here, most of the things that we were, there are a lot of kernel options that were preemptive RT first, that are not preemptive RT anymore for long ago, and people just forget about it. Like ftrace was an RT thing.
The whole tracing thing was RT only.
Yeah.
Yeah.
So all those things, that was when the RT started merging with the kernel.
But I think one of the first things
Piece
was
by
log
piece.
depth, because back then it was like 2.6 or even 2.4, where the machines locked up because SMP wasn't like that common. So machines locked up randomly and no one knew why, and log depth started pointing out the problems. And this came out from the RT tree back then. High resolution time was also one of the things back then.
So do we have questions from the audience? then?
Yeah. Is there any question that you guys would like to chat about?
We got one. Great.
Well, I thought I think this topic was what's next, right?
Yep.
So,
What's next?
and you said that, as you said, I like it's, this is about building community, and we have this great community.
Yeah, we do.
So what do you guys see as the next, I mean, okay, the big lift has been up, doing the work, and it's going to be upstream. So what else is the community working on next? I think we had really good discussions in the room today about, there's many other things around tuning, education, but I'm curious what you guys think that the community should focus on next.
I have ideas, but then, okay, we've figured out what the requirements are implicitly for real time. I'd love to have them surfaced explicitly.
I think that we, as a community, have been focused a lot of this in the scheduling latency as the problem for real time, myself included. But now what I'm seeing is that this is working, the community is working fine, and this is let's say, something we can rely on. And the challenge on real time are also moving to the scheduling of not only one task per CPU that will give you the highest latency, but for multiple tasks sharing the same CPU and trying to get not latency, but response time. So one example was today, like the idea of consolidating multiple systems into fewer CPUs. And then we start going towards the scheduling side. Like, how do I share a CPU with multiple real-time tasks, with most of the tasks making the deadline? That's one point that I see. And then we go to deadline scheduling and more problems with lockings, because when you start having tasks sharing the same CPU, the problem with locking becomes more evident. And what I'm seeing that there is development being done that goes right in the kernel regular workflow, not necessarily on the RT anymore, because RT is part of the kernel. It's the work with the proxy execution that we need to figure out a better way for priority inheritance. And one thing that I will start working with is having multiple schedulers inside that deadline reservation, so we can share a CPU among multiple tasks using the sched deadline parameters.
But just that you mentioned it, is proxy execution going somewhere?
It seems, what I'm seeing is that there's part of the patch set that it seems that they split the patch set as a set of pre-requirements for it.
So it's being worked on, would you say?
Yeah.
What's next? Future.
Yeah, that's what's next. Yeah.
So it's being worked on, and it's supposed to be worked on? That's my question.
No, people are working on it.
Uh-huh.
So it's present, not the future.
Well,
yes,
it's not
to
done
be merged.
yet, so it's future.
Yeah, okay.
The future. Oh, yeah, to be merged in the
I mean,
future.
we're talking about it for years now, right?
Well, yeah, but now we're working on it.
So that's like a big step forward.
Right?
That's like a big step forward.
No, yeah. Also the throttling problem. We started talking about it in 2016, 17.
But I wasn't like aware that this is like that big issue.
The throttling?
Yeah.
No, it is. Now, like for example, on our use case, those people that were running the NFV use case here, where you run a single task on an isolated CPU, they run the task, they would like to run it 100% of the time. What is happening with us is that there is always a K worker that will end up on the CPU, and this locks the system.
You will see warnings or something like that.
Do you see when it's too late?
Is it?
Yeah, that's where we're getting. So with the DL server, we boosted the CFS for like, because the SCAD deadline, we can give like very high resolution slices of time. We can set the CFS to run like 20 microseconds every second, just to unlock the situation.
But you do it like over and over again, right?
If it depends on how often something will go to the isolated CPU.
Because then you might just want to get rid of the worker.
Yeah, for example, one of the cases is with VMstat. When you dispatch the workload.
But didn't we fix that part? Where the
No, not yet.
Didn't MM say we don't care about accurate statistics, we can just avoid it?
No, they're still happening.
Seriously?
I think so.
I thought MM said we can.
I think that patch set from Marcelo was not yet merged. But we have other use cases like people dispatching the workload on isolated CPUs, and then there's the script that dispatches the real-time workload, and the script hangs on that CPU because the real-time workload preempts it.
That's correct, yes.
Well, certainly real-time is very unpopular in industrial operations, and that's one of the main use cases, as an automotive potentially now, and things like that. And so safety and the Linux kernel and safety, and making real-time be accessible for people doing the analysis for safety is something I think will come in the next few years. And that's why the ELISA project's been working with the PreemptRT. In fact, I learned about safety mostly from the real-time project and Thomas, lots of talking with Thomas about it. He was basically educating me for several times about why this is important, et cetera, et cetera. And so, you know, a lot of my education came from talking to Thomas about safety. And I think, you know, it's because most people that care about safety are using real-time in some fashion. And so the fact is now we need to start surfacing out the information so that they can do the right analysis. And so there's various people working on that. So I think that'll be starting to come. That's one thing I'm aware of.
Yeah, and this is the problem start going to the end of the execution of the task, not only for the scheduling. The scheduling is the minimum thing that we need. But we need to place the task to run and see the end of the execution. And then we start going to the real-time analysis for the scheduling.
Yeah, determinism.
Yeah.
Okay, so years ago we merged the SCAD DL.
Yeah.
Does anything happen on the front, or is it like all done, all stable, all fancy?
What we have now is stable. We haven't seen like critical bugs for quite a while.
Okay.
Yeah, so people can use. It's just that it's too restrictive yet, because we don't. So, if we have the real-time throttling enabled, there's the setup that limits the CPU. We end up engaging one thing that is the admission control of the deadline scheduler. The admission control, the idea is that it will not allow the system to run more than the CPUs that the system has, right? And this limits ourselves to the scheduler being global. That is, the scheduler will put the tasks on all available CPUs in the root domain. So you cannot set affinities for the real-time tasks. And that's too restrictive for most of the workloads because people would like to set affinities. It's a basic tuning, right?
Okay.
Nowadays you can bypass that, disabling the real-time runtime, the throttling argument. It's not only throttling. You can disable the admission control, and you can manage and place the deadline tasks wherever you want. That works, but what we are seeing in the research is that doing global isn't efficient anyways. So we are trying to pursue ways to partition the system on other methods. And that's a task that I have on my to-do for quite a while. It's the same with partition the scheduler. DDL server is a pre-requirement for that.
Okay.
Things are moving.
Things are moving. Are there places where people can get engaged? So if there's someone that's really interested in real-time problems, how do they start engaging and helping?
Well, I've seen the talk here and there, what people went through to set up the RT system. And I thought it was way easier because most of the things I've seen was like, this is obvious, this is well known, this is, it's written in the trace. But apparently, it would be nice to have it like documented everything in one place. Like, what does a problem look like? What tools look for, and what's like the things to do.
There's a question there. Okay. Just say we have a good starting point on the real-time tuning guide for Red Hat. It's open, but
Yeah,
I see your point. It's focused on the use case that we have. That's not everybody else's.
And it has this TuneD thing, which is...
It works.
Yeah, but it does things that are not documented, right?
It's documented in Python.
No, it does... We have to look up...
Yep, so it's more a remark on that than a question. You raise a very good point. It feels like people are rediscovering again and again how to set up an RT system. From my point of view, the thing that had the most impact in the past few years was RTLA, because we finally have a way for users who are not very knowledgeable about what's going on the system at the hardware level, at the kernel level, the scheduling level, and also people who are not familiar with tracing at all. We finally have one tool to get easily all of the information that we need to do the investigation. And to me, the fact that PreemptRT gets merged at some point is not going to change that much with that. It's just applying a patch, enabling the option. For people, it's just going to be one less step. But the road that is going to be left in front of us is going to be more, in my opinion, about educating people about that. How do we configure everything properly and what's going on in the hardware system. So the thing I would like to see is more tools like RTLA or easiest way to do some analysis about what's going on for people who don't really want to know about what's going on behind the scenes. And I don't say that to be mean about people who work on the PreemptRT patch, because it's really awesome work, but it's not something that the users can even sometimes just understand or want to understand. So that was just a remark on that.
And I didn't pay a beer for him to make this thing.
Okay.
I think that, so that's getting back to the point that things takes time, right, to be done in the right way. The RTLA idea was born in 2010. So that was when it came to my mind, the question was like, okay, intuitively I know that the PreemptRT has a bounded scheduling latency. How do I abstract it to the point that I could convince the real-time academic community that there was a bound, right? So how can I explain them? Because once I explain them how the bound is composed, I can build tools that I can explain why things are broken, right? And from that to the tool to be merged in the kernel, it took 12 years, right? So, but along the way, we extracted a lot of cool things.
Yeah.
So I had to learn how to do tracing efficiently, to try to explain what was the response time of a task on Linux. And then just doing tracing wasn't enough to explain. Then I had to learn a formal method that I could describe the system. And then I created this model of how the PreemptRT works. And from that, I took out the RV subsystem that I need to put more work on it. But I took that as an output. And then I took the formal definition of the scheduling latency. Explain, okay, this is how the latency is composed. And I took out a proof of concept tool that's still not on RTLA, the RTSL, when I talked on 2020 at Plumbers. And that tool, it was cool, but it was depending on things that are disabled by default on kernel, like the preempt IRQ disable tracer, because it added too much overhead. And then I had to think, okay, how can I take the benefits of that abstractions from that tool, but still make it usable without having these options that we cannot enable? And then it came with the idea of the timer lot. And once I had timer lot, it was able to extract the auto analysis, because the analysis was built on this composition of tasks. It took a long time ago, but something that I hopefully will not regret, because once we regret of editing something in the kernel,
Yeah, and I think it's good to see that take time, but I think that's one of the things I wanted to maybe spur conversation here and there is because what you just said, I've heard from many other people, right? And I think, I just want to say that we talked about this earlier, but I think because it's close to being mainstream and because of some things in the industry that are aligning to this need and wanting to be, some of us, wanting to be on mainstream Linux and security, I think the need is quite urgent in things to diagnose, to benchmark, guides on how to, because I think, I've seen and we've heard of many people who are now, kicking the tires from outside. And, there's, as you said, it's not just about learning about the scheduler preempt RT, it's about all of the other things that we've discussed today. So is there some way we can focus the community on these more? And as you said, I think you're trying to go there with the, how do people get involved? How do we get, because you've been working on, sounds like you've been, and maybe on the RTLA, but how do we get, more people rowing?
No, but I think that the point is that once we get something right in the kernel, it creates momentum. And this momentum pushes people to work together into a good solution for everybody. That's why sometimes things take time to get into the kernel. Because you need to make something that is good for all possible use cases. And then this creates momentum and creates more people developing now. Adding more analysis to RTLA now, it's just user space C code processing trace. It's easy to contribute to RTLA. It's user space code mostly. So, and I think that's the same thing that happens with...
As my point is, you're talking about the development process takes time, but I think maybe when I'm talking about focusing, we had a great presentation over there from someone. He said, he did a whole bunch of work, and he said, if I would have known about RTLA, which, whatever years ago, he would have saved him a lot, right? So, part of community is awareness and other things as well.
That's why we have this event.
That's right. That's right. That's why we're trying to basically, and it's being recorded, so hopefully we can point people at it when people don't, aren't aware of things. And certainly LWN does a very nice job of writing things up for us. And I've used that search feature many a time to double check some things. Thank you.
No, but that's it. You see, there was many people here discussing the same thing. Right. You see, most of the presentations were hitting the same. We need to enable this option. We need to disable that option. And that's the part of the community sharing knowledge, and that's one of the motivations for this event. It's sharing these common things that we have.
Right.
Okay, so I'm going to be a little bit contrarian here.
Of course, Tim, of course.
I tried to convince some people in the space sector that Linux was real time, and they were not buying it. And I think there's a messaging problem. The last time I went to a presentation about RTLA, it seemed like it was a tool that showed you all the different ways that Linux failed at real time. Because it identifies all these things like in the kernel or other places where the real time, didn't go according to plan, and sure, there's ways to fix it, but it's like that's a counter message, right, to the fact that that Linux is a real-time system.
On that presentation, the guy doing the presentation was trying to force cases. no, but seriously speaking, real time is not only about latency, but response time, and about defining well your workload, right? Mm-hmm. So you need to understand your workload and understand how to fit it into the execution model of Linux. We need the tools to help to identify when Linux misbehave, right? But that's the common process for every operating system. If you have an operating system that, because of the workload, it's failing on the metric, you need to find ways to show it. But with a correctly set up system, Linux is reaching, for sure, millisecond granularity with space for error. There are tools just...
But to come up with a different example, if you buy yourself a 100G networking card, you most likely don't get 100G out of it right away. So you go ahead and you start tuning. You may be looking at BPF and XDP to get the last bits out of it. It's not working out of the box as it is, I think. Because this is what I've seen looking through the pages, like how to split the queues, how to do this, how to put the workload through it. So it's not like a unique solution just to buy a 100G card and be done. The same thing applies mostly to RT as well.
And I'll also basically put a plug in for one of the real-time analytics project members, OSADL, who spends a lot of time actually characterizing systems, running real-time, and being able to let you have more visibility into what's actually happening. That's an area and that's part of why they've been supporting the project. So if you've got certain parameters you want to do, they can basically bring the long test, and they've got a whole infrastructure for really understanding what's going on a certain version and things like that.
With CPU isolation, like trying to create the best scenario, you create CPU isolation and run RTLA timer.now on a paper that we are working on a RHEL operating system. It's not an embedded thing. It's RHEL, huge chunk of kernel, right? With RHEL, with CPU isolated, we were reaching like less than 10 microseconds scheduling latency, right? With the tuning. Then if they start putting their real-time workload on that CPU, then they have a clean space to start working.
Okay, so I'm sorry, but the impression is that an expert, after checking 100 different tuning options, can get it to a good latency. And so, I mean, that's the impression that's out there.
And then we have tools like Tunity that helps.
Oh, come on.
And we have RTLA. Yes, it requires some level of expertise to make things work properly. But things are getting better. I will start showing better results. On
so speaking of the topic of education that was raised, and given that Preempt RT should be mainline soon, isn't it the time to have, like, for example, the Yocto project, which is also a Linux Foundation sponsored project, has an amazing set of documentation, hundreds of pages that are really helpful. Maybe it's the time for like a detailed book or a detailed manual about the topic, given how hard RT is.
The thing is, we do have a wiki, and I point people towards the wiki, and there are people coming on the mailing lists, coming with a problem, and I say, is this working for you? And they come back and say, yes, thank you. And then I ask them to update the wiki, and this never happens. And I think that people using RT from the industry have different mentality compared to those running software using Yocto, right?
I mean, it's the same people.
Any volunteers are welcome to help us get the documentation better, is I think what the answer is.
It's not because John is here, but I think the best place to put these details is in the kernel documentation.
I agree completely. It needs to be upstream in the docs.
RTLA document, the timer.tracer, RTLA, RV, all the documentation I'm placing inside the kernel, because it has a bigger notion of value if it's in the kernel, because it creates this momentum of the Linux kernel, and it helps people to contribute more.
And it has the higher quality threshold. And as it multiplies, hopefully the maintainers have reviewed it too.
That's why I placed the RTLA inside, tried to put inside the kernel, because it raises the bar of quality.
Right, that's why we tried to get some of the ELISA work up into the kernel too, in terms of, methodologies for looking at.
Sometimes I get some emails saying, Daniel, you shouldn't have done that way, and I need to work a lot, but it raises the bar.
Okay.
So you think we should add the Preempt RT documentation?
To the kernel directly, yes, please.
Or for example, we have many parameters here that are on the command line, right?
Right.
We could maybe add it in a tag saying, oh, this from a real-time documentation pointing, maybe being an index of options, because there will be things on the real-time that will be on the documentations on the RTLA, part on the SCAD deadline, part on the kernel command line, part on RCU. It's maybe an index of pointers on the kernel documentation.
Basically a primer on here's how to go find out how to go do it and point all the pieces that need.
For example, SCAD deadline, and this would help contributing to improve the kernel documentation.
We could split kernel parameters.txt and have a real-time parameters.txt. Kernel parameters.txt is so long, and all those real-time parameters are in there, but you have to read through a lot of it and have a lot of knowledge of what you're searching for to use it. Yeah.
Or maybe grouping the current by topic.
Grouping by topic.
Because duplicating source of information, same information, you create inconsistencies, and in one side because people might update that and might not update that.
We could do it with the HTML formatted output, maybe.
Yeah,
I don't know.
The Docker experts might have a better answer. But I would, for example, on RTLA, I use includes because there is one main page that uses the same options from the other, so I include in the same file. So when I change the option description, I change on all the main pages and all documentations. Maybe we could use an include thing but duplicating the same information on two spaces is prone to inconsistencies.
I think
Hopefully
another approach.
the documentation maintainer liked what I said. Maybe he has some comments.
Yeah, I think another approach would be like completely. Pardon me?
Do you have a mic?
I have one. Don't you hear me? All right, didn't want to interrupt the other comment, sorry. Much of the kernel documentation, like kernel parameters.txt, was basically thrown into a big pile in the kernel. And this is something that I've been, since I took over maintainership 8 years ago, have been trying to fix by trying to organize our documentation with the reader in mind, so that if you're a particular sort of audience, a particular reader with a certain sort of task, that you can go to the same thing and you don't have to plow through a whole bunch of stuff that is just not totally intended for you, but for someone who's like trying to modify the driver or whatever like that. So, I mean, great ideas. I encourage help in doing this. This has been a multi-year effort and we are far from done with it. But I think that like splitting out some RT-related manuals would be a very good idea.
Yeah.
Yeah, sorry. I mean, another approach is to, from my point of view, it would be better to eliminate the number of kernel parameters, because from a point of view, from the viewpoint of a secure boot system, it's not always possible to dynamically adapt the kernel parameters. And my impression on the parameters regarding the use case is choosing the right parameters depends on your workload. And if you're trying to provide a platform for customers where you have multiple use cases, you cannot always choose the parameters ahead of time for your platform. So moving to more like parameters which you can modify during the runtime would maybe a better idea.
But that's a trend in the kernel in the kernel developers, right? It's just that sometimes removing a kernel parameter requires reworking part of the kernel, and this reworking part of the kernel takes time. That's the ISO CPU case.
How are we doing on time here, actually?
No, I think what he asked for is to have this.
I think we're getting close to time.
Okay.
But keep going.
Yeah,
Finish.
I think the question was if you could have some of the parameters switch at runtime instead of boot time. And depending what the parameters are, not all of them are compatible with this. Simply because you need to make a decision at boot time, so either you fire it up or you don't fire it up at all.
Yeah.
So this is tricky. For instance, you can switch the preemption model, but you patch the whole kernel, and this can be done only once. But you cannot switch the timer model via command line. This is only compile only. And if you could switch it make it switchable, it would be also one of the things that you could do only at boot time. And for some parameters, this thing applies. So it's boot time only.
But the trend inside the kernel is to making this thing dynamic. It's just that it needs to rework fundamental parts of the kernel. And when this happens, it's harder because we cannot break what is now if we want to keep our job. So that's why I think it takes time. And the time showed that that's the correct way to do, right? That's why Linux is what it is.
Last question, I guess?
Yes, my question is about the documentation of things that are not so relevant for most of the users, but for some it's quite relevant, like the kernel threads. So at least I don't know of a single documentation page where you see all the kernel threads, their priorities, what they are for, what is important when I change the priorities of these kernel threads. So having something like that would be really, really good.
So this got cleaned up a few releases ago. So either you have scat other, or you have RT priority 1, 50, or 99. And this is it. We don't have anything in between. And 50 is like the middle one. 1 is, we don't care. It's not that important, but it should be important and everything is get other. And then you have 99, which is like super important, and you shouldn't touch it at all. We don't have that. Oh, come on.
DCFS is now a deadline task with the new throttling. It will be.
Okay, so this thing, come on.
So you need a bit more. I mean, this is a good step forward, but you need more if you actually have to pave a way from your I/O event to your real-time workload. So you have to know which of these middle thingy is under which condition important for my OPAS. I can do the tracing-wise thingy, but if I have to trace my system first of all to do that tuning, then comes also this reconfigurable thing on the radar. So how do I react on that if my workload is changing? So it's a little bit more complicated.
Yeah,
I mean, it's getting way simpler, but it's not quite there yet.
But this depends, like what hardware do you have, and what scheduling do you have, and what file system do you have, and this is not unique.
Yeah. It's easy. It's just we remove all the code, and then all the options are just one. The Linux is complex because it handles, come on, it handles the cell phone, it handles the real time, it handles the thing on space. Hopefully in the future they will believe on us. It has options because it has many use cases. That's a good thing, people. That's a good thing.
Okay,
Motivated Daniel.
I do think we are pretty much out of time. So you are the last question.
Okay.
Yeah, so it's not a question. It's just I want to share the experience like for my presentation in the afternoon. So I'm not a kernel guy or the Linux person. So, but I just want to share my experience when I debugging that issue. I refer a lot to the ChatGPT to find out the meaning of the kernel, the options related to the kernel. If you don't work on this, it will be confusing to understand what that means. So I'm just curious if you have like consider about having plan like integrating the solutions to some of the AI tools. If I want to, for a user like me, okay, I want to debug the latency issue. I just type those words and okay, it prompts okay some suggestions and hey, you could try maybe the RTLA tool and something like that.
The point is ChatGPT doesn't know RTLA. I asked him. He doesn't know, and then it points you to the wrong direction. But if you have searched on the kernel docs about the real scheduling latency in the search button on the kernel documentation, it will point you there.
Well, I think we need to curate the ChatGPT and basically say if it's getting it wrong somehow and be able to get feedback.
I tried ChatGPT how to debug RCU latency. It was a supercazzola. It's an Italian term to say yes. It missed it.
Next,
Sorry
no, it's okay. So we need to teach ChatGPT to say, read the kernel docs.
Yes, that's a good starting point.
Okay, well, thank you very much, everyone, and thank you to our panelists.
Congratulations.
Congratulations, my friend.
It went well. It went well. You see, life